Hi and welcome to this course. It's amazing to have you on board, and I can't wait to dive into building AI-powered workflows and agents together with you. Because in this course, you'll get all the fundamentals you need, all the core concepts you need to understand to build your own AI-powered workflows and agents. We'll explore the difference between workflows and agents, we'll dive into important theory concepts, and most importantly, I'll show you plenty of examples, concrete code snippets I prepared for you, which I'll walk you through to get you started building your own workflows and agents. And that's the idea behind this course. The idea really is to give you all the core knowledge in only a few hours so that you can finish the course in a weekend if you want to, so that you can transfer that knowledge to any project or any programming language you might be using in your day-to-day work so that you can start building your own workflows and agents. And therefore, let's not waste any time. Let's dive in and let's start with maybe the most important question. What exactly is an AI workflow and what's an AI agent and how do they differ? So, what are AI agents and how exactly do they compare to AI workflows? It, in the end, depends on how you define it. One possible definition is that AI workflows are deterministic sequences of steps. So you have a program that automates a certain task or problem, and that program simply executes multiple steps. It might open a file, read that file content, transform that content, and save that transformed content somewhere else. In that sense, every program could be called a workflow, I guess. But if one of these steps, or multiple steps, use AI, use large language models, for example, we can call it an AI workflow. It automates a certain task with help of AI. Now, AI agents, on the other hand, are autonomous, which means you set up an AI agent by writing a program that uses an AI model, a large language model, to plan the execution of a certain task and to then also execute that plan. So the AI model creates a plan, and then you, the developer of this program, give it access to tools that allow the agent to also execute that plan. What's also important to understand, and I'll get back to that, is that the large language model, the AI itself, will never execute anything, though instead it will just call tools you expose to it, and you'll see how that works throughout the rest of this course. But the AI doesn't act on its own, instead it just acts based on which tools you give to it. That's really important. The key difference here is that you have less control, because with an AI workflow, you have a high level of control. The sequence of steps is always the same. You know exactly what happens in each step. With AI agents, if we're talking about them as defined here, that they act autonomously and that they make their own plan and use the tools you give them, such AI agents, of course, don't give you a lot of control. You only have a low to moderate level of control because, of course, you control the instructions, you control the tools. The AI can't do anything it doesn't have the tools for, but you don't know which tools are going to be used when. And therefore, AI workflows are useful for tasks where you have known inputs and outputs and where you know in detail how a certain problem should be tackled. AI agents, on the other hand, are useful for tasks where you have unknown inputs or outputs and where you don't know exactly how a certain problem should be solved. Now, in reality, in my experience, most problems can be solved very well with AI workflows, and therefore those controlled workflows are preferable because you know exactly what's going to happen there. But certain problems, like a customer service agent, are better solved with help of AI agents because you don't know what the customer is going to ask for example. But this is just one way of defining it. In reality, you'll often encounter the term AI agent being used for every program or every step in a workflow that solves a certain problem with help of AI. In reality, AI agent often just means something that uses AI. For example, later in this course, we'll build a multi-step workflow where we generate a blog post, have AI evaluate that blog post, and where we then also generate a thumbnail and a LinkedIn post based on that blog post. And this clearly is a workflow. We'll have a sequence of steps here, if we take my definition here. But many people would call this an agentic system where we have multiple AI agents working together. We have a blog post agent that writes the blog post. We have an evaluation agent that evaluates the blog post, a thumbnail agent, a LinkedIn agent, and so on. And that is, of course, totally fine. It just brings me back to these questions and the fact that the answers to these questions simply depend on how you define the term AI agent. This is one possible definition, but very often any program that uses AI will be called an agent too. So now that we have a first idea of what AI workflows and agents are, before we get started writing our own code and building our own workflows and agents, I want to point you at one AI agent you likely already interacted with. And that would be ChatGPT, or Google Gemini, or xAI's Grok, or Anthropic Claude, because all these AI chatbots actually also are kind of agentic. Because all these chatbots nowadays have access to tools. Now, you might need to enable those tools, but they will also often smartly choose to use certain tools depending on your query. For example, if I ask ChatGPT something like which new AI models got released over the last 2 weeks, it will actually go ahead and search the web. And what's happening here is that it's using the Search the Web tool that's provided by OpenAI to ChatGPT. So behind the scenes, it's using a tool to fulfill your request, to answer your question. And that's exactly what an AI agent is all about. It got some instructions by OpenAI behind the scenes. You don't see them. It got some tools like this web search tool, but also other tools. And then it got some input, your message, and it produces an output. And it's an AI agent, not a workflow, because of course OpenAI, which built this program, which built ChatGPT, doesn't know in advance what you're going to ask for. So of course it wouldn't make sense to always perform a web search, to have a clearly defined sequence of steps. Instead, it makes more sense to have a flexible system here, which simply is able to use various tools depending on the received input. So that's a good first example for an AI agent we all probably already interacted with, maybe without knowing. But of course, again, in this course, we'll build our own workflows and agents. So now that we have a first idea of what agents and workflows are, we're ready to get started. And this is a very short course. It's just a few hours so that you can finish it in a weekend if you want to, or whenever you have time. And the idea behind this course is that I give you all the core theory, all the important concepts you need to understand, and that I'll show you concrete examples with code I prepared for you. We won't write that code together. We'll only write some code together when I get you started with using large language models in code in general, when we get started with using the OpenAI API in code in general. That's some code we'll write, but thereafter I'll give you pre-built code snippets so that we can focus on the core things that are going on in that code, and so that I can save you some time, because if you don't want to, you don't have to follow along, of course. You can just watch and learn. You don't have to follow along and write the code. Instead, the idea really is that you'll get the knowledge you'll need to build your own AI workflows and agents after finishing this course. And for that, in the next course section, we'll start by diving into AI workflows. However, that section, the next one, will be the important foundation you need to then also build AI agents. So don't skip it. Instead, please watch it, because many of the concepts you'll learn there will matter again once we start building agents. The AI agents section, which comes thereafter, builds up on that AI workflows section. And you'll also see that often the difference between agents and workflows is quite blurry. So both sections matter and build up on each other. Thereafter, in the last section, I'll also show you how you could use a third-party package, Crew AI, to save some time and not write all the code on your own, and instead build workflows and agents with a third-party library like that. That's the idea, and therefore, let's not waste any time. Let's dive right in and let's get started writing code and understanding code and seeing plenty of examples. So let's get started building AI workflows. And this section here will be the foundation for building AI agents as well. Because as you'll see, the difference between workflows and agents is really more of a definition question and not so much a hard boundary, at least in many cases. Because in this section, we'll dive into all the essential building blocks you need to know, no matter which kind of AI automation you're going to build in the future, no matter if it's just a workflow or an autonomous agent. Now we'll start by taking a brief look at no-code versus with-code solutions, though this course here is all about writing code. It's not about no-code solutions, but I want to show you this alternative as well. But thereafter, we'll get started. We'll explore how you can use large language models programmatically, specifically how you can interact with OpenAI's models programmatically. That'll be the example API we'll use throughout this course. But we'll also explore how you could use open, locally running large language models instead of those proprietary models offered by OpenAI, Google, and so on. And whilst the focus of this course will be on those proprietary models, and whilst I will use those OpenAI APIs in pretty much all examples, you will also learn how you could replace those paid proprietary models with open, locally running alternatives depending on your workflow. We'll also explore how we can work with structured input and, more importantly, request structured output by AI models and what that exactly means. And we'll explore how we can manage the control flow of a workflow, how we can run steps conditionally or repeatedly. We'll also see how we can add a human to the workflow, for example, to request extra feedback at a certain point in time. And we'll also take a look at integrating third-party services. We'll make sure that our workflow can also send Slack notifications, for example. So, plenty of topics to cover. As mentioned, it's the foundation you'll need for the next course sections as well, and therefore, let's not waste any time, let's dive right in. So, let's start by taking a look at how we can build AI workflows and agents. And here we got two main options, two different approaches for building workflows and agents. We can either do it without writing code or with code. And the difference, of course, is that for no-code approaches, you don't need to know how to write code, obviously, because that's the entire idea here. For with-code approaches for this course, therefore, you do need at least some basic programming knowledge. By no means do you need to be an expert, but basic knowledge is required. Now, when it comes to no-code approaches, there are many tools available. For example, N8N is a very popular one. And attached, you'll actually find a link to a resource that gets you started with using N8N to build no-code workflows and agents, in case you're interested in that. I also cover this in my complete ChatGPT and generative AI course, where I dive deeper into working with N8N and AI in general. But for this course, we'll focus on the with code part. But of course, there you can also use any programming language you want. You're not limited to one specific language. Now, speaking of limitations, there are some when using the no-code approach though, because there you're limited to the features provided by those tools. Now, to be fair, these tools are quite capable, but certain goals or tasks are actually easier to achieve and implement with code if you know how to write code than without code, because you have full flexibility and no limits if you know how to write code. And that's therefore, as mentioned, what we'll focus on in this course. But as also mentioned, attached you find a resource that also gets you started with the no-code approach in case you're also interested in that. Now, as you know, this course is about building workflows, AI workflows, and AI agents. That's what we'll focus on. And therefore, we'll need to access AI models, large language models, programmatically, because we'll write code and we want to use these models in our code. Therefore, it's important to understand that there actually is a difference between a large language model and an AI application that leverages a large language model. Because typically, as an end user, you don't directly interact with a large language model. If you're using ChatGPT, if you're asking a question there, you're technically not directly sending that message to a large language model. Instead, you interact with an application that uses a large language model internally. In case of ChatGPT, you're interacting with the ChatGPT application that was built by OpenAI. And that differentiation is important because the AI application, ChatGPT, for example, contains both application logic, so the code written by you if it's your application, or the code written by the OpenAI engineers if we're talking about ChatGPT. And that logic can be about all kinds of things, like parsing the user input, managing a chat history, maybe interacting with third-party services to fetch something from Dropbox or to get an email or send an email. It might generate documents and do anything you want if it's your application. But that anything you want part also includes interacting with a large language model. And ChatGPT, the ChatGPT application, does that internally. It interacts with OpenAI's large language models, and you can do that too. In ChatGPT, you can actually tell the application with which model it should interact. If you're building your own AI application, and AI-powered workflows and AI agents are just AI applications in the end, you therefore also might want to interact with a large language model. You actually need to if you want to integrate AI. And therefore, you interact with models provided by OpenAI, Google, xAI, Anthropic, or any other provider. And you do so by using their APIs, which means you're going to send requests to their servers, which then trigger their models under the hood, and you'll get back responses generated by their models, which are running on their servers. And all these providers, OpenAI, Google, and so on, they offer APIs you can use and you can interact with to interact with their models through these APIs. And you'll find detailed documentation by each provider for their APIs and how to use them. You'll find details on which models you can use through their APIs. You'll find details about the pricing, because using these models by these providers is not free. These are paid models, so you're paying for all the tokens you're sending to them and for all the tokens you're getting back from them, and I'll get back to that. And you'll find instructions on how to interact with their APIs, often for different programming languages, but also for generic requests which you can send from any programming language. And that is what we'll take a very close look at over the next lectures, because that's exactly what we'll do. We'll send such requests to interact with those APIs. And that's therefore how you build AI applications and how you build AI workflows and agents. You have your logic, and then you reach out to some large language model provided by some provider like OpenAI through their APIs. Now, when it comes to using large language models in your own applications, there actually is an alternative to using the large language models provided by OpenAI and so on, for which you have to pay, which I showed you in the last lecture. You can use these proprietary models, but you can actually also instead use open models. Now, these proprietary models are the models that are hidden behind the APIs provided by these providers, so which can only be used through their APIs and where you have to pay for the usage. And OpenAI, Google, Anthropic, they all offer their own proprietary models through these APIs for payment. So you pay for the usage. You can't run those models locally. Now, to be fair, it would be hard technically too, because these are large models that need really powerful, very capable machines and PCs. But even if you had such an extremely powerful computer, you would not be able to access those models because they are proprietary. They're not available for public access except by using their APIs, where you have indirect access to them. Now, that also means that you have less or maybe no data privacy because you have to send all your prompts, all your questions, all your data to their servers for every single question you have, for every single interaction with the large language model. And therefore, you have only very limited control over what they do with that data, and it definitely leaves your machine for that request. Now, open models are a popular alternative. Specifically, we're talking about open weight large language models, which means these are large language models that have been trained by certain companies like Google or Meta, but also the DeepSeek model would be a very popular one. These are models that have been trained by companies, and these companies then published the results of this training process, the so-called weights that make up the large language model. The great thing is that you can run these models locally, for example, with help of tools like Ollama, which is a tool that's available for macOS, Linux, and Windows, which you can download to your system, and I'll show you how that works in the next lectures. And then you can use this tool to run all kinds of open large language models on your system. And what's really great about these open models is that most of them are published in different sizes, so with different amounts of parameters. Now, in general, you can say the more parameters a model has, the more capable it is, but even models with a low amount of parameters can be great at certain tasks like summarizing text, understanding text, or generating text based on some other input text, as you'll also see in this course here. And that's important because this number of parameters, which here is shown in billion, is related to the amount of computer memory this model needs in order to run on your system. And you can roughly double these numbers and take the result in gigabytes to have an estimate for how much memory you need. So to run a 1 billion parameters model on your system, you will typically need around 2 gigabytes of memory, preferably GPU memory. So the larger models, especially if you have hundreds of billions of parameters, are typically very hard and difficult to run on your system because you typically don't have the hardware for that, but smaller models can be run there, and again, as you'll see, they are often more than good enough for many of the tasks you might want to perform with help of large language models. And Ollama makes running such models on macOS, Linux, and Windows a breeze. And it's also worth noting that Ollama isn't the only option. There also are other tools, but Ollama is amongst the most popular options. And actually, I got an entire course where I dive much deeper into running such open weight large language models on your computer, but in this course, we'll also use them as an alternative to the proprietary models. Because the advantage here is that they are, of course, free to use, you don't have to pay for the usage, and you got 100% privacy because you're not sending any data to any servers. Instead, it's all running on your own computer or on your own server, for example. Now, to be very fair, it's important to recognize that the best models, which offer the best performance, are typically the proprietary ones. But there also are very capable open models available. For example, DeepSeek R1 is a good example for an extremely powerful and capable open model that was published in early 2025. And there are many others as well. But there are also smaller models, which is important. Otherwise, you wouldn't be able to run them on your laptop, for example, if they take up too much memory. There are smaller models available, which are maybe not as powerful as the best proprietary ones or like DeepSeek R1, but which are more than good enough for many of the tasks you want to perform, as you'll also see in this course here. And therefore, that's an alternative you should know about, and an alternative we'll also use in this course besides some proprietary models, because it is an interesting alternative which does offer significant advantages. Now, in order to finally write some code, we of course need a development environment that allows us to write code. And for this course, I'll use the Python programming language because it is extremely popular in general, but also especially for AI-related development. It has a very simple syntax, it's easy to learn, and therefore it's perfect even if you don't know Python or if you don't know a lot about Python. That's no problem at all if you got some programming experience, some knowledge which you need for this course, no matter in which language, then you'll be able to follow along with Python as well. And of course, what you'll learn in this course can also be applied to other languages because you can access all these models, proprietary and open, not just through Python, but in the end, through any language you want, because we're just going to send a bunch of HTTP requests to various APIs. Now, we'll also need a code editor, and for this course, I'll actually use VS Code and Cursor. VS Code is an amazing free code editor that's available for all operating systems. Cursor is not really available for free. It's very limited if you don't pay for it, but it's also totally optional. It's just an amazing AI-powered editor which can make writing code a bit easier, but it's absolutely not a prerequisite for this course. And then, as mentioned, to programmatically interact with large language models, we'll need to interact with some models through APIs or with locally running models with help of Ollama, and we'll do both in this course. Now, when I use proprietary models, I will use OpenAI's models, so the GPT models. And that's, of course, totally optional. Again, what you'll learn here will apply to all models. You can interact with all models. You'll just always need to take a look at the documentation of these models and the APIs provided by these model providers to understand how you can use these models, which kind of parameters you can tweak, and so on. But for all the examples in this course, we'll use OpenAI, APIs and models, or the locally running open large language models with help of Ollama. So finally, let's get started writing some code. And for this, I'm in a brand new empty project, empty folder, opened up here in Visual Studio Code. And I'll start by creating a Python project by running UV init using the UV Python project and package manager. Now, UV is a tool you won't have on your system by default, but you can install it on all operating systems. Attached, you find a link to the official installation instructions. And the great thing about this UV tool is not just that it's free to use, but that it's an extremely capable Python package and project manager. It'll automatically create and manage a virtual Python environment on a per project basis, ensuring that any third-party dependencies you install don't pollute your global Python installation. It's extremely fast and overall just an amazing tool. Therefore, as mentioned, attached you find a link to the installation instructions for macOS and Windows. And once you got that tool installed, you should be able to run UV init to create a new Python project. Of course, you can also create a Python project in any other way you want, though, because we won't really use any more advanced UV features. We just need a Python project here. So out of the box here, I got a project with a bunch of files, most importantly, a main.py file, which is pretty empty initially. And I'll use this file as a foundation now to build a first basic AI-powered workflow. We'll build this first AI workflow using the OpenAI API, so using a proprietary model. And I'll get you started with how to interact with this API and the core things you can do with that API. Now, in order to access that API, you will need an OpenAI account. That can be your ChatGPT account, but typically you'll visit platform.openai.com, and then there you can sign up for an OpenAI developer account, so to say. Now, you will need to pay for using OpenAI. So you will need to buy some credits the first time you sign up here, for example, $5 in credits. And once you did that, you can go to your dashboard when you're logged in, and there you'll be able to monitor your usage. So how many requests you send, how much you interacted with the API. You can also set a budget here, which is independent from the credits you bought. But here I'll edit my budget and edit this to set it to just $5 to make sure I get alerted if I approach this budget here. Under billing, you can see your current credit balance. Here I bought $5 in credits. And you can, of course, enable auto recharge or buy more credits once you need them. And back on the documentation page, where you find detailed instructions for all the different APIs OpenAI offers and what you can do with them, there you'll also find a pricing page where you learn how much you're going to pay for the different models. And you'll always have input and output tokens here. And these prices then are per 1 million tokens. But of course, they're not just charged in 1 million chunks, but for every single token, but then only a fraction of that is charged, of course. And you can see there are some models which are super expensive. And of course, these prices will change over time. So by the time you're viewing this, the models and prices will already have changed very likely. But you will see that some models are cheaper, some are more expensive. Of course, some models are more capable, others are less capable. So it really comes down to choosing the right model for the right task to avoid spending unnecessarily much if you don't need it. And we'll also explore that in this course. It's also worth noting that, as I mentioned, you could use other APIs, other models by other providers as well. For example, you could use Google's Gemini models through the Gemini Developer API. And in that case, you would need to create an account with Google, and you should also visit their documentation, their pricing pages, and so on to learn how you can use their models and their APIs, because every API works a bit differently, typically different parameters, different options that can be sent. And therefore, it's definitely important to take a look at the detailed documentation for the API you plan on using. Though I will mention that many providers, like Google, for example, actually also offer at least some OpenAI compatibility, which means you will be able to send requests in a way that's very similar to how you send requests to OpenAI, even though you're not interacting with OpenAI, because OpenAI has shaped the de facto standard interface for interacting with AI models, and that's why many providers offer some degree of compatibility. And again, the official documentation of these providers is the best way to learn more about that. Here, I'll focus on OpenAI. Now, as a last step, you will also need to create an API key, no matter which provider you're using. And that API key is, in the end, your way of authenticating with that provider from inside your code. Because soon we'll start sending requests from inside our code. And of course, we need some way of telling OpenAI, Google, whichever API we might be using, that it's us who already paid our $5 here. And we do tell the API that it's us by using a unique API key that's unique to us. And you can always create more API keys if you need them, like demo. And it's then this key which you'll need to copy and use in your project. And of course, any API keys you'll see in this course will be deleted by the time I'm done recording, so you don't even need to try them. Because, and that's important, if anybody gets access to your API key, if you accidentally share it, if you, for example, push it to GitHub, then those people can send requests to those APIs, to the OpenAI APIs, for example, on your behalf. And you will be paying for that. So you want to avoid that. So make sure you never accidentally expose your API keys. And if you do, definitely make sure you delete them as soon as you notice that you shared it so that it can't be used anymore. That's also important. Okay, and with all of that out of the way, we can now get started writing some code here and build our first AI workflow. So to get started here, I'm in my main.py file, and in there I want to build a very simple workflow that will in the end take some user input, then use an AI, a large language model, to generate a post for X, so for the X platform. And then I want to output that post so that I could then copy and paste it and share it on X. Now, that's of course not the most amazing workflow ever. We'll see more complex and useful workflows later in the course, but it's a great first workflow to get started and to learn how to interact with the OpenAI API. So as a first step, I will get the user input by using the input function in Python. What should the post be about? And I have this very specific message, what should the post be about, because I'm not building some random chat app here that should be able to handle all kinds of questions and inputs. Instead, I'll build a specialized workflow that's only about producing X posts. It's not about chatting with the AI in general. That's why I have this very specific question, and everything in that workflow will be optimized for generating X posts. That's important. That's a crucial difference between building a versatile chat application like ChatGPT, which you could also do, and a specialized workflow which aims to perform one single task with or without AI. In this case here, with AI. So we got the user input. The next step now is to generate an X post with help of AI. So I'll add a new function here, generate X post. And here I got my user input, which will be a string. And adding types like this is optional, by the way. It is a feature of modern Python, but you don't need that. And I plan on getting back a string here. And then in here, we need to call our large language model, send this to the large language model. And we'll do that soon. For the moment, I'll just pass. And then down here in main, I'll get my X post by calling generate X post and passing my user input to it. And thereafter, I'll output this. And actually, I'll split it across multiple lines here, like this. So that's the plan. Therefore, this here is now the important part, because now we want to reach out to a large language model. As mentioned, I'll use the OpenAI API here, and therefore a good start is to take a look at their documentation, because as mentioned, that's always what you should do as a first step. Now here in the overview page, I get a first impression on how I could send a request. Here using the curl tool, which is a tool that comes pre-installed on Linux, for example, but the shape of this request shows us how we can in general send it with help of any language and any library we might be using in any language. So here, for example, the goal would be to send a request to this address, which is the address of the OpenAI API. Then we would specify that we're sending some data formatted as JSON. We would include this authorization header, which includes our API key, which is important. If we forget this, we will not get a response, not a success response anyways, because we need to authenticate and tell OpenAI who's sending the request. And then we would attach some data where we specify which model we want to talk to. And again, that is important also from a pricing perspective. And we would send our input, our prompt. Now you can also send more complex prompts. You can see that if you dive a bit deeper into the documentation. You can, for example, send an entire history of messages where you can also include developer or system messages, as they used to be called in the past, that provide some general instructions to the model. You could also send an existing chat history that may include past responses by the AI, so that the overall context is available to the AI for the new response it will generate. Because, and that's the important part here, for every request you're sending to the model, you start a brand new session with it, so to say. So it doesn't know anything about past questions you might have sent. If you send this input, it won't know anything about prior conversations you had with it, unlike ChatGPT. But that's the case because ChatGPT is an AI application built by OpenAI, as explained before. And therefore, it's this ChatGPT application that, for example, manages the chat history. And it's this application that always sends this entire history to the large language model, which, as mentioned, is something you can also do. But you are in the driver's seat. You control what's sent to which model. That's the key takeaway here. But first things first, I want to send a request like this. So, as a first step, I will actually install a library, which I can do with UV add here, since I'm using the UV tool. And the library I want to install is the requests library. Of course, if you're not using UV, you can also pip install requests, like you probably did in many other Python projects before. So here I'll use UV though, and install this requests library. And with that installed, I'll import requests here, and then send my request here. So I'll get back a response by sending a post request, because you actually need to send a post request to the OpenAI API. And the URL to which I want to send the request is this URL here. Now, just as a side note, the OpenAI API actually changed over time. In the past, there also was another API available. And you can still see that, at least at the point of time where I'm recording this, if you dive into the documentation, and then you might have a drop-down here, which allows you to switch between the responses and the chat completions API, which is the previous standard API, so the old API format. There, the URL was different. It was API, openai.com, and then at the end, /chat/completions. And the way you would send data to it also differed. Now, with the more modern, newer responses API, this is the address you send the request to /responses, and the format of your data also changed. Now, in many guides, you will see the old API format, and AI tools like GitHub Copilot also may suggest the old API. You can use it, but the recommendation is to use the modern one. So this address, which you find in the documentation, the responses API. So that's what I'll do here. Now we also need to attach some data to this request, which with the requests package can be done by specifying the JSON parameter. So that will be the payload of my request, which should be a dictionary. In there, we need to specify a model, and I'll fill that out in a second, and my input. Again, I could send a more complex chat history if I wanted to, but to get started, we can also just send an input string. Just a simple prompt. Now I'll also fill that out later. It's then this payload that should be added here as data to this request. Now I'll split this across multiple lines to make it a bit easier to read, like this. Now we also need to add some headers, which again will be a dictionary of headers we want to add, so metadata we attach to the request. And that will be the content type header, and then this authorization header, which includes the API key. So the content type header is, of course, straightforward. The authorization header is a bit more complex. It is bearer as a hard-coded text, and then our API key. And that's the API key you find in your dashboard once you're logged in. So here I'll create a new one. And again, it will be invalid once you're viewing this. So I'll copy it here. And then, of course, I could paste it in here. And that's how that looks like. It's not a good idea to put your API keys directly into your code though, because again, you shouldn't share it with anyone. And of course, you will often share your code. So having the key in there is not a great idea. Instead, what's typically done is that you add a .env file, an environment variable file. And in your gitignore file, you make sure that this is not included if you're using Git for version control. So that this env file is not pushed to GitHub, for example. And then in there, in this .env file, you can set up a variable that might be called OpenAI API key, and then store your key here. But this will now only ever live on your system. It's not pushed to GitHub. So that's why it will be saved. And then you can use that key in your main.py file through that environment variable. Now, to make sure that this environment variable gets loaded, you want to install an extra package, which is called python.env. That's a package that loads .env files and puts the environment variables that are defined in those files into your actual environment so that they're available in your code when it runs. With that installed, what you would do is you would import from .env the load.env function, execute that at the beginning of your script so that it runs as the first thing, because that is what will load those environment variables. And then with that done, you can access your environment variables. So here I would now get my OpenAI API key by using Python's built-in OS package. And then there is a getEnv function which can load the value of an environment variable into this program. The name here, OpenAI API key, of course must be the same as you specified here though. With that, that will be available, and now OpenAI API key can be used here like this. And that's now the base setup we need. Now we can work on the model and the actual prompt. Now, for the model, pricing, of course, matters, and the power of that model, so to say. And it simply depends on the task you want to perform, how capable the model must be. Now, of course, when it comes to OpenAI, all these models are quite good, but some are better, of course. O3, for example, this model is better than 4o mini. And you can tell that it's better because it's way more expensive. This costs $2 per million tokens, input tokens. O4 mini is just 15 cents. So it depends on the task you want to perform. For example, if you want to summarize some text, a small model like 4o mini is typically enough. If you have a complex planning task that benefits from reasoning and advanced thinking, so to say, a more complex model like O3 or maybe even O3 Pro might be needed, though that's really expensive. For my example here, I'll go with GPT-4o. It's more expensive than 4o mini, it's also a bit more capable, and actually even more expensive than O3, but not as expensive as the advanced thinking models. Now, it is totally up to you which model you want to use, and by the time you're viewing this, some of these models and prices will already have changed. At least that's quite likely. So it's always up to you to decide which model you want to use. And OpenAI, for example, actually even has a guide that helps you with selecting the right model, which you find attached. You also might want to take a look at that. So in my case, it will be 4o this here, and I'll copy that, this identifier, and paste it here. So this identifier here should match this identifier. And now we can work on the prompt. Now, the prompt could be our user input, which we received, right? But that actually would be wrong because we're not building a generic chat application. Instead, we're building a specialized workflow, as I mentioned before, which means it aims to do one thing and one thing only, but do that one thing well. So what we're getting here is actually the topic a post should be written about. So what the user will enter in response to this question is something like, open large language models like Gemma are amazing because they allow you to run large language models locally on your laptop. Which is not really a great prompt. It's a statement, not a question. But that is what the user would probably enter when getting asked for a topic the post should be about. So the prompt we want to send to the model should actually augment this initial user input. So I'll add a new prompt variable here and use a f string, which allows me to dynamically inject content into this string, just as I did it here with the OpenAI API key. And use triple quotes so that I can conveniently write a multi-line string here with line breaks without messing anything up, primarily for formatting reasons. And now we want to craft a prompt that's optimized for this workflow. We want to do some prompt engineering here. It is an important skill. It's also a skill I talk about in my ChatGPT and Generative AI Complete Guide course, but it's in general important also when building automated workflows as we're doing it here. For example, we can assign a role. You are an expert social media manager. It's not too bad. And you excel at crafting viral and highly engaging posts for X, so for the X platform. I'll also add formally Twitter here to provide some extra context to the model, which has been trained based on past data, a lot of data where X was called Twitter. So I'm providing this context to make it clear that X is Twitter. Because again, in the training data of the model, it's likely that many posts it saw were actually tweets on Twitter. So that's a role I want to assign here. And then I want to provide some instructions. Your task is to generate a post that is concise, and that all sounds good, and tailored to the topic provided by the user. I will also say avoid using hashtags and lots of emojis. A few emojis are okay, but not too many. Yeah, that sounds good. Keep the post short and focused. Structure it in a clean, readable way using line breaks and empty lines to enhance readability. And then, very important, we have to insert the topic provided by the user. So actually, I'll rename user input here to topic because that's a more meaningful parameter name, because in the end, what we get here is a topic entered by the user. And then I'll say, here's the topic provided by the user for which you need to generate a post. And then what I like to do is add delimiters like topic XML tags here, which is nothing you have to do, but something that often helps the quality or which helps produce better results with large language models. That is something I experienced and something you'll find in many guides and best practices out there. You could also use other delimiters like triple dashes, for example, to clearly separate the user input from the rest of the prompt, but I like these XML tags. Again, technically they're not required though. And then here I'll insert that topic. And that's now the actual topic we received as a parameter. And this is now the overall prompt that should be sent to the GPT-4o model through the OpenAI API. Now we'll get back a response here. And of course, in order to extract data from that response, we need to understand its structure. Thankfully, that is again something where the official documentation helps us, though here under text and prompting, I see an example response I might be getting back, or a part of that response to be precise, because here we learn that we'll get back an object that has an output property. And in this output property, we'll have an array of objects, of dictionaries in Python, where every dictionary has some data inside of it, like, for example, a content key, which again contains an array. And then in there, we have objects with the actual text we got back from the API and from the model, therefore. And this response has such a complex shape because you could potentially also get back more complex responses if they, for example, include both text and images. For now, we only expect to get back some text though. So we should be able to get the response text by calling the JSON method on this response object. That's a method provided by the requests package, which we're using for sending the request to extract the received response data and convert it into a Python object. And then we can call get on that received dictionary, which we get in the end, and get the output property, because that is what we learn here, that we have such a property. And then in there, we will have this array of dictionaries. So in there, we can access the first element, because right now we only expect to get back one message. This will then be a dictionary where we'll have a content key, which will hold another array. So I want to access content. And then since this is another array, I also want to access the first element in there, which will be this element here. And there we'll then have a text key, which holds the actual text response. So here I want to get my text. The default value here for content, if nothing is found, should be an array with an empty dictionary inside. So that's how we can extract the response. And we'll also see an alternative way of interacting with the API, which is a bit easier later, but this is the bare bones approach that works with any language because we're just sending a request, and that is what will always happen under the hood, even if you are using a simpler approach later. So now here I just want to return my response text like this, and that should then be that X post which we output here. And with that, we hopefully now have a finished first basic program which takes some input, generates an X post, and outputs that X post. So now, to see it in action, I'll open my terminal and now run this Python program by running python main.py or python free main.py if that doesn't work for you. Or here, since I'm using UV, I can also run uv run main.py. And now I'll first get asked for the topic, so the topic for that post. And I'll say open LLMs are amazing since you can run them for free on your local system. They're often more than capable enough for many LLM-powered tasks you may want to perform. So that's my topic. It could be shorter, it could be longer. This is what I chose here. And now if I hit enter, this will be put into our enhanced prompt and will be sent to the OpenAI API. And as a result, I got a generated X post, which is this one here. And that is an example for our first basic workflow. Obviously, as mentioned, not super complex, but you can see how you can interact with that OpenAI API and what makes this a workflow. It's not a generic chat. Instead, we have a clearly defined task here. We create our own prompt. We do some prompt engineering here, and we use that as a basis, as a foundation to have a reusable workflow, because now I could, of course, run this script as often as I want and generate more and more posts based on whichever topic I provide here. And that also includes short topics like AI will change the world, and I would also get a post for that. So in the previous lectures, you learned how you can send a request to the OpenAI API to interact with an OpenAI large language model. Now, I walked through all these steps in great detail because, of course, the goal of this course is to teach you how to work with APIs like this and to show you what's happening under the hood and what makes this here a workflow that specializes on one specific job. Now, as mentioned before, there are many things you can configure about those requests you're sending to the API, also depending on which API provider you're using. The official docs are the place to learn more about that, because in there you can also learn more about assigning different roles to your different messages, about sending a chat history, You can learn how to send images to the API to have the large language model analyze an image, or how you can get it to generate an image, how to work with audio and speech, and much, much more. Now, many of these things you'll see throughout this course. We're just getting started here, after all. But it's always important to dive a bit deeper into the documentation if you plan on using a specific provider or model, because of course, these APIs, the capabilities, and the capabilities of models of different providers change all the time. So use the official documentation, it is your friend. Now, when working with APIs like the OpenAI API, constructing requests on your own like this is absolutely fine. The advantage of this approach is that you can send a request like this in any programming language. Of course, the exact code would have to change. You would be using other packages, the syntax would be different, but the URL, the headers, and the payload would always be the same. That is, after all, the API you're interacting with. But when you're working with officially supported languages, if you want to call it like this, you also have the option of using an even simpler approach for sending those requests and extracting the responses. Because besides constructing those requests on your own, you can also use the official SDKs, the official software development kits. And it simply depends on the provider, which SDKs for which languages are provided. OpenAI here, for example, has examples for Python and JavaScript, though there, for example, also is an official Go library if you would be working with Go. It's just not in the examples in the documentation. But again, it depends on the provider which SDKs and libraries for which programming languages may exist. But here, if I do switch to Python, I can, for example, see that instead of constructing this request manually, as I did it before, I can also install an extra package, the OpenAI package, which is provided by OpenAI, then create such a client object, and then use that client to send a request, and also, and that's the best thing here in this example, to also extract the response in a way easier way than what I had to do here. So instead of diving into some nested objects in arrays and so on, when using the official SDK, there is an output text field on the response, which I can access to get quick and easy access to the received response text. So therefore, that's what I'll do here. I'll add the OpenAI package. I'll install it here into my Python project with UV-add. And with that done, instead of importing requests to send my own requests, I'll import OpenAI. Or specifically from that OpenAI library, I'll import the OpenAI class. This then allows me to create a so-called client by simply calling OpenAI like this. And that will then also automatically detect that OpenAI key if it's available in an environment variable called OpenAI API key. So I actually don't need to manually load it like this anymore. I just need to make sure that the .env file gets loaded. So this line is still important. And you could also always manually set the API key like this if you, for example, had an environment variable that had a different name. But if you're using this name, you don't need to do that. You can just create a client like this. And then with that, in generate xpost, I still want my prompt, but this part here changes now. Because now we can simply get a response by using that client. And now the suggestion here is actually for the old API, so I don't want to use that. Instead, now it's client.responses.create. And then to create, we pass at least 2 parameters where we tell OpenAI which model we want to use, and then again our input, our prompt. So here for the model, I'll again use GPT-4o, just like before, and for input, I'll still provide my prompt, also just like before. And now we can return response.output text, because that's now a little convenience field we get on this response object, because this response is now coming from that OpenAI SDK. And therefore that's now a bit easier. It's a simpler approach of sending that request and handling the response. And what's really great about this OpenAI SDK is that it can actually be used with many other providers as well, because it allows you to set a base URL, which you don't need to set if you're interacting with OpenAI, but which you can set to a different value if you're interacting with the API by some other provider which supports this OpenAI format. Like, for example, Google with their Gemini models. In their documentation, you also learn that you can use that same OpenAI package we're using here, and you just change that base URL to the Google API URL here, and you set your API key, the Gemini API key then, and then you could use this OpenAI SDK just as you use it with OpenAI, though, at least right now, when I'm recording this, Gemini only works with that old API format. Again, the Gemini documentation is the place to go to learn more about that. But it's worth keeping in mind that the great thing about the OpenAI SDK is that it can be used with some other providers as well. Here, I'll use it with OpenAI though, and therefore that's all we need. So if I now save this again, and I then run my script again, I can again provide a topic. Like, for example, building AI workflows with code gives you way more flexibility than using no-code solutions. And again, a request will be sent. That's the same as before. It will essentially do the same thing as before, just behind the scenes, now with help of the SDK. And I get a nice little post, which I could now share on X. We did now get started with building a basic AI-powered workflow. And I chose this workflow because it's not super complex and it allows us to understand how we interact with the AI API, how we can use the AI model in our application. It is a specialized workflow because it's only about generating X posts, but it can be improved. And that is a crucial part of building AI-powered workflows. You wanna try to improve them, and often that means improving the prompt and performing prompt engineering and simply testing which prompts produce better results. Because right now, the X posts I get are still kind of generic. If I run this and I try to get a post on this topic, LLMs unlock many new business models, I will get a post, but it's pretty generic, maybe good enough, even includes some hashtags here, even though I told it to not include that. So maybe it's not what I want. Therefore, prompt engineering matters. And one great way of achieving better results in many situations is to perform few-shot prompting. So besides assigning a role and having general instructions and using delimiters, few-shot prompting is one of the most powerful prompt engineering techniques that's able to dramatically improve the results you're getting. And few-shot prompting simply means that you include some examples into your prompt. So here, for example, I can say, here are some examples of topics and generated posts. Now again, I'll add a delimiter. It's technically not required, but I like to have it here to make it clear or clearer to the model where the examples start and end. And then I'll have another delimiter, topic, and generated post. And then I'll come up with some topics and posts I might want to share. So here I added 2 examples, and you could add more. And every example has a topic. So that would be the part the user would enter, the user would provide. And then I have a generated post, which is what I expect the AI to generate. I have that for each of my 2 examples. And even though it's just 2 examples, we should already get better results just because we added them here. Now, one thing I will add is some extra instruction here where I say, please use the tone, language, structure, and style of the examples provided above to generate a post that is engaging and relevant to the topic provided by the user. Don't use the content from the examples. So some extra instructions to hopefully ensure that it's really just the style of the examples that's picked up and not the content. And as mentioned before, prompt engineering is about simply testing different things and finding out what works best for you. So now we got a quite complex prompt, but that is one key part of building AI-powered applications. Prompt engineering is one key element of that. So now with that, if I again run this and I want to get a post about ShadCN, which is a UI library in web development, being the de facto standard for building web UIs in 2025 and telling people that they should learn it. If I set this as a topic and I send this to the AI models, I get back a post that is more in line with the posts I provided here as examples. And again, you could provide more and also tweak other parts of the prompt if you're still not happy with the result you're getting. So prompt engineering is important. What's also important to understand is that you're building this workflow, you're writing the code. I mean, that's the main thing of this course. That means you're in full control of that code. And that also means, for example, you don't have to put your entire prompt into the code like this. For example, these examples I added here are a great example, no pun intended, for content you could outsource into a separate file. So for example, I could add a post examples.json file, and in there add a list, an array of JSON objects, and JSON is really just text that's formatted in a certain way. And then in there, for every object, I could have a topic, which would be the text I have here, and my post that should be generated for this example, which would be this text here. I just need to make sure that I don't break it with all the line breaks. So I'll make sure that this is all one line here, like this. And I can also add the second post like that. And then with that, we can simply load that file into our program and dynamically generate this prompt. We can load this file in read mode, extract those examples, and dynamically construct this examples text, which we need down there in the prompt, like this. And with this examples string here, which includes all these examples, we can inject that into our prompt here, just like that. Simply to keep that prompt a bit shorter and outsource these examples into a separate file. Is that something you have to do? No, but it is something you can do because it's your code, you own it, you build your workflow. So with that done, we can of course still run that script just as before, define our topic, and get a post that is in line with our examples, because those are still loaded, just in a different way. Of course, you did not take this course to just learn about simple, basic, one-step workflows, though the foundation, of course, is important. But here, we now got an example for a more complex, multi-step workflow, where we'll actually also use different AI models in different steps. And you find the updated version of this workflow, the updated main.py file, also attached to this lecture. This updated version no longer asks for a topic as an input, but instead for a website URL. It then goes ahead and fetches the HTML content of that website by using the requests package again, sending a GET request to that URL. And I'll say right away that this approach will not work for all websites, because there are many websites that have mechanisms to defend against requests like this, or websites that don't load all the content initially with the first request, which this request here would be, but which instead also load some content with client-side JavaScript code, for example, after the initial page load. All those websites would not really work with this approach. But there are many websites where this approach will work. So this will give us the HTML code of that website. And we then use this HTML code to actually extract the core content of the site. Because if I use my personal website as an example here, the HTML code of one of my posts can be seen if you inspect the page source, looks something like this. Not horrible, but quite a lot of code. I can scroll quite a bit to the right here. And of course, since it's HTML code, there are many HTML elements, CSS classes, and lots of stuff in there that's not relevant to us humans. The core text, which you see here, only makes up a part of the actual source code. But it's the overall source code, the overall HTML code, that's fetched by this step. Therefore, I also need a step that actually extracts the core content, the core text of this website, the core content that would also matter to us humans. And that's what extract core website content does. This step now actually leverages a large language model to perform this extraction, because detecting the core text inside of a sea of HTML elements is non-trivial, especially if you want this to work with all kinds of websites, not just one clearly defined website. So you don't know the HTML structure in advance. And these are exactly the kind of situations where large language models shine. So again, I'm using the OpenAI SDK here, and then I'm using the 4.0 mini model here instead of the 4.0 model. I'm doing that because this 4.0 mini model is super cheap, way cheaper than the 4.0 model. And for tasks like summarizing text, extracting data from text, this 4.0 mini model is more than enough. It's absolutely capable to handle those tasks. But these are also the tasks that typically involve a lot of tokens. I mean, again, if you take a look at this source code, all this text here, all this markup is fed to the large language model. So all these HTML tags also consume tokens. So having a very cheap model is definitely important here, especially since, as mentioned, it's more than capable enough for this task. I then have a basic prompt where I instruct the model to extract the core text, excluding navigation, footers, and other non-essential elements from the received HTML code, which is received as input here. And then I return that extracted text. So hopefully the text that's relevant to humans. Once I have this core content, I have another step here, which actually summarizes this content, because in the previous step, I extracted all the text as it appears on the website. Now I want to create a summary based on this text. For that, I again use 4.0 mini, because again, for tasks like extraction, but also summaries, it's awesome and it's cheaper than other models, so that's why I'm using it. Have a simple prompt, pass my content, the extracted content, to it, and then hopefully get back a summary which I return. And it's then this summary which I again use to generate an X post. I also log the summary and the core content for debugging purposes. That's my workflow here. Again, leveraging large language models, but different kinds of models. 4.0 mini for extraction and summaries, but for post generation, I'm still using 4.0. And therefore, here, I can again run this script, paste in a URL, like here, the URL from my own website, from this article. And then it'll go ahead, fetch that content, send it to the large language model. And this can take a while because it is a lot of content to parse and process. So now the model is doing its work, trying to extract the core content. Here we go. That is the core content it detected, the core text it extracted from all that HTML code. Looks pretty good to me. Then it's summarizing it. Here is the summary, a bunch of bullet points, because in my prompt I told it to prefer bullet points. And then I got my generated X post based on that summary. And that's of course a pretty amazing workflow, because this now allows me to paste in any URL with a caveat, because as mentioned, this method of extracting HTML will not work for all sites, but for many sites it will. And therefore I can paste in any URL and just see whether it works or not, and then get a post and a summary based on the website content, which is a pretty amazing workflow, in my opinion. And most importantly, it's a workflow that shows you that you can combine multiple steps, where every step may or may not use a large language model, and that you can also use different models for different tasks. So we saw this multi-step workflow in action here, and that's of course an important workflow, an important milestone in this course. Now, one thing I want you to note is that some people would call these different steps agents. Now, I previously defined AI agents as autonomous things, autonomous programs that create and execute a plan based on instructions and possibly using tools you exposed to them. And that is the most mainstream definition you'll probably find out there. But it's worth mentioning and keeping in mind that some people also refer to individual steps that perform a clearly defined task and that use a large language model for that task as agents too. So extract core website content could be called an agent because it has a task, take an HTML input, extract the core content, and it performs that task with help of a large language model. So we could also call this workflow a multi-agent system if you want to sound fancy and impress others. Now, it's totally up to you what you want to call this workflow. I'll just call it a workflow, but just so you know it, some people would call every step here an agent because it has a clear task, and many of these tasks also use large language models, and it's up to you what you want to call it. Now, I've mentioned it before in this course that besides using these proprietary models by OpenAI, Google, and so on, you can also run open large language models locally on your system or on some server owned by you. Now, it depends on your hardware, but for example, on relatively modern MacBooks, you can run many of these models without problems, and also on many of other devices. As also mentioned before, you can use a tool called Ollama for this, and attached you find a link to that. And this tool is available for free for all major operating systems. You can download it from their website ollama.com. Once you did install it, you can run the Ollama program from inside your terminal or command line. And when you do run this program, you get various commands you can execute to download and run models on your system. And you can visit the Ollama model catalog to get an idea for which models you can use. For example, the Gemma 3 models, which are Google's open models. So Google does not just have its paid Gemini models, which you can access through their API, but they also have the Gemma models, which you can use for free with Ollama, for example. Though it's worth noting that all these open models typically also come with a license, which you should Google and check before you start using it to find out if you, for example, can use the model commercially. Many are allowed to be used commercially, but some are more restricted. The Gemma 3 models are quite permissive, though. Now, the Gemma 3 model here comes in various sizes and even has vision support, so it can even analyze images, as a side note. And which size you want to use simply depends on your hardware and the task you want to perform. The bigger, the better, but the more memory is required. I mentioned before that you can roughly take this number by 2 to get the amount of memory you need on your system to load and run this model. So a 4 billion parameter model would need around 8 gigabytes of memory, plus some overhead. So for example here, I can run Ollama pull Gemma 3 4B ITQAT to download this specific version of the Gemma 3 model. Now, how do I know this identifier? Well, on this Gemma 3 page, you can either use the identifiers you see here, or if you scroll down a bit, you will see that in case of Gemma, there are these quantization-aware trained models, which don't exist for every open model, but which do exist for the Gemma models, which are simply models which are even more optimized to run on consumer hardware. Again, I dive a bit deeper into all of that in my dedicated open large language model course. So in the end, that's the command I ran here, just not run, but pull, to not start a chat session with that model, but instead to just download it. And you need to download it in order to use it on your system. Now this can take a while. I did already download it, which is why it's quite fast. And once you did download it, you actually don't need to do anything else. You just need to make sure that you ran Ollama at least once so that the Ollama process is up and running. Because when that process is up and running, Ollama also spins up a server that runs on your system, so on your machine, which is not available to anyone else but only to you on your computer. And this server exposes an API which you can use to communicate with an open model that's running on your machine through Ollama on your system programmatically. So you can then send, for example, post requests to this endpoint and configure the request to use this locally running model for whatever you want to do. And that's what I did here. Attached, you find this open py file, which is very similar to the main py file from before. It has the same multi-step, multi-agentic workflow, but which is now not using OpenAI in any step, but instead only Ollama or the Gemma models specifically. So here in the get AI response function, which I added for this open version here, I'm sending a request to my local machine and then to API generate, which is this endpoint exposed by the Ollama server. I then provide some information about the model I want to use, the prompt, that I don't want to stream the response, but instead get it in one chunk. And then here, numctx, this controls the context window that's being used. Because Ollama by default does not open up the entire context window these local models can use. They do have quite a bit context window, but by default that's not unlocked because all this context window also takes up space in memory. Which is why I set a rather small context window size of 4,000 tokens here as a default, but this can then be changed from anywhere where this function is called. Like for example in extract core website content. Here I'm using this 4 billion parameters version of the model to extract the core content from the HTML content. And I'm ramping up the context window size to 20,000 tokens here because all this HTML content is rather long and I want to make sure that I don't run out of context window. For summarize content, I'm then using the very small 1 billion parameter version of the model, which I also downloaded in advance onto my system with Ollama pull. And I'm using that for summarizing because, again, these small models are actually really impressive and good at summarizing tasks. Also at extraction tasks, but here I found that the 1 billion parameters model was not quite good enough for this task, which is why I went up to 4 billion, which is still pretty small. But then I'm using 1 billion here for the summarization. And then actually, I'm using the 27 billion parameters model, which is the biggest Gemma 3 model for generating the post. Because when it comes to creative work, to generating text, my experience is that the bigger models tend to perform better. They follow instructions better, they pick up examples like the ones I'm providing here better, and that's why I'm using the bigger model here. And therefore I have a multi-step process using different models, but I'm only using models that are running on my machine. So again, if I run this open py file, I can pass this URL to my website to it. It extracts the content and then the core content of the website. And this will take a bit longer than using OpenAI because this is now running on my machine, on my laptop, which is not quite as capable as OpenAI's servers, so it will take longer, but it will work. So here's the extracted core content, and as you can see here, for me, it actually did include some HTML content, which I technically did not want in there, but it shouldn't be a problem because it did grab all the text, which is the key thing. And the summary it created does look good, so no problem that this was in there. It's a very small model in the end, so errors like this can happen. The question just is if they're problematic. And then here's my tweet based on this content, or post, I should say. And that's now all handled by large language models that are running on my system. And depending on your hardware, you can do the same. When building more complex AI workflows or agents, it's quite common that you're not just dealing with plain text, that you want the AI to not just generate plain text. And thus far, in all the previous examples, we did only deal with plain text. Our posts were text, the HTML content was text, everything was just text in the end. But it is quite common that you actually want to work with structured output, that you want to work with data that must have a certain shape, and you want AI models to generate data in that shape. That's why the OpenAI API and many other APIs, including Ollama for running models locally, offer you structured outputs as a special output mode. Now, when using OpenAI's API, it depends on whether you're using Python and JavaScript, in which case you got a simplified way of defining your target data structure, or not. And I'll start with the more complex approach, which you can, of course, also use when you're using Python or JavaScript, and then thereafter I'll show you the simpler approach. But I'm starting with the more complex one so that you see what's happening under the hood, and so that you're also able to use this knowledge if you're working with other programming languages which do not have the same support. Here I'm in a brand new AI workflow, and you find this updated main.py file attached. And this workflow is all about accepting some user input. So the idea here is that you run this script, and in the command where you execute it, you provide a path to some file or folder, specifically to a folder that contains PDF documents or to a single PDF document. Now, these PDF documents which I prepared here are simply invoices, which I edited a little bit, but in the end, invoices as you could receive them, for example, from Cursor or from X. And the idea behind this workflow here is that we can provide a path to the PDF documents, to the PDF invoices specifically, that should be parsed. The workflow then checks for whether this path exists, if we point at a single file, and if that's the case, if it is a PDF document or not, or if we point at a folder, in which case it tries to find all PDF documents in that folder. And then it actually goes through all these PDF files, and for every PDF file, it extracts the invoice details. Actually, first it gets the text from that file, and that's not done with help of AI, but instead with plain old boring code. Using a special Python package, the PDF reader package, or the PyPDF package to be precise, to extract the text content from that PDF document. And that's important. We could also upload a PDF file to OpenAI. They do support that, and many other AI providers do too. But if we can save that extra AI request, it's typically a good idea to do so, because you're paying for every request you're sending to these AI models. So if you just want to extract some content from a PDF document, you can also just do that locally. And that's what I'm doing here. And it's then that extracted PDF content, that text, that's sent to a large language model in this extract invoice details function. Here I'm again crafting a prompt where I tell the model that it's an expert at extracting document data or invoice data specifically, and then I insert that PDF content. I also instructed to return the response as a JSON object without any extra text or explanations. When working with OpenAI, this instruction should not necessarily be needed, but it also doesn't hurt to increase your chances of getting back data in a valid JSON format. Because that's really important. These AI models are token generators. They generate text. Now, conveniently, JSON formatted data is just text, but it is text that has a certain format, a certain structure. And it is possible that an AI generates text that looks almost like JSON, but that isn't technically valid JSON. That's why extra instructions like this help, but if you also use another trick, which I'll show you in a second, you have an even higher chance of getting back valid JSON data. And that other trick is to specify this text input here when sending the request to the OpenAI API. And that's what you learn in the official documentation when viewing the curl example. There you see that you can provide this text parameter, which then describes the shape of the data you want the AI model to generate. And under the hood, with this extra information sent to OpenAI's servers, OpenAI and its program, you could say, that's wrapped around their large language models, try to make sure that the models do generate appropriate output that has this format. Now, this may look a bit scary at first, but it is in the end a standardized way of describing the shape of the data you want. You must have a text parameter with a nested format parameter, where you then assign a name to your data schema. This name is up to you. The type then must be JSON_schema. You must have a schema key, and that then is another object, another dictionary here in Python, where the type must be set to object, where you must have a key named properties. And then in there, you have another nested dictionary where you describe the properties, the fields of the data you want the model to generate. So for example, that I want to have a vendor field, which itself holds a nested object, where I have a name, an address, and a tax ID, since I'm extracting invoice data here. Additional properties must be set to false then, and required must include all these property names to make sure that they are produced by the model, they're not optional. Customer then is another data field, which has some nested data, the name of the customer, address, tax ID. And then I extract the invoice number, date, total amount, and tax. And that's just some shape I defined for my example here, since I'm dealing with invoices. Now, every field here has a type and a description. And the description is important because that is what tells the model in the end which data should go into that field when it generates that field as an output. So you send your prompt to the model, which contains the PDF content in this case. And the model should then take a look at this content and extract data from that content and map it to this schema down here. And these descriptions simply tell the model which value goes where. That's why they are important. Now, when it comes to defining that schema, you actually have quite a lot of options. In the official documentation under supported schemas, you learn more about the supported data types, the supported properties, and you see more examples on how such schemas can be defined. And it will depend on the API you're interacting with, which exact properties and restrictions are supported. For example, if you're interacting with Ollama, you should also consult their documentation, to which you also find a link attached to this lecture, to learn how it can be configured to return structured data. Now, with that all set up, we should get back some text output by the model, which actually contains data in such a JSON format, which is why I then try to transform this into a raw Python dictionary. And that's what this function then returns, and that is what we then receive here. These invoice details are the transformed AI response. And then here in this example workflow, I insert this into a database, because again, that is something you might want to do. So I have a simple SQLite database here, which is a SQL database that can run locally on your system without any special setup or anything like that. You don't need to install any software. It will create that database in a file in this project. It sets up a table with all the data I want to store, and then I insert my data here. And of course, you could do whatever you want with that extracted data. You could hand it off to another step that uses a large language model. You could save it in a CSV file. Whatever your workflow needs to do. So therefore here, if I now run this file, I don't run it now by just hitting enter. Instead, I provide that path to the document or the documents that should be loaded. In my case here, that's this PDFs folder. And here we go. It now starts extracting. It sends that data to the large language model. And what we're getting back here, that is the response by the AI model, but it has a certain structure, a certain shape, and that is, of course, the shape we defined here with this schema. This database file also got created, and if I open that with a special extension called SQLite Viewer, which I installed into my editor, I can see that all that data was inserted here. That's looking quite good. And that's therefore an example of working with structured data. Now, as mentioned, when working with Python or JavaScript, you can actually make your life a bit easier though. When you need structured outputs and you're working with OpenAI and you're using Python or JavaScript, you can actually avoid the hassle of defining this schema as I showed it to you in the last lecture. You can still do that, as you saw, but you don't have to. Instead, when using Python, you can use an extra library called Pydantic to define a class that describes the schema of the data you want the AI model to generate. So here I created an invoice class, which extends the base model class, which is provided by Pydantic. And I define a bunch of fields in there, which in the end just means I describe those fields. The rest will be done behind the scenes by the OpenAI SDK and Pydantic. Now, the vendor and customer fields are actually classes themselves, since I'm working with nested objects here, nested dictionaries later. And I brought back the OpenAI client here, the OpenAI SDK. I no longer send requests myself anymore. Instead, in extract invoice details, I now still have that prompt, but the rest of the logic is way simpler, as you can tell. It's way less code because this entire schema definition disappeared. Instead, I just set this special text format parameter here in the parse method, which I call on client responses. Previously, we used client responses create. Now, if we want to deal with structured data, if we want to get structured data, we use client responses parse. And that parse method supports a text format parameter, which takes a Pydantic class as an input. So my invoice class here. That's sent to the OpenAI SDK, so to say. And behind the scenes, that SDK will derive that schema as we defined it in the last lecture from that class here. And therefore, we don't have to do that on our own. Instead, this will now generate a response. We can then get the parsed response data in this output parsed property on the response object. And that will be an object of our class, which we defined here. So we'll get back an invoice object here in output parsed. And it's then this invoice object, which I'm using down here to insert it into the database. For that, I'm using the model dump method, which is provided by Pydantic to turn this invoice class into an ordinary dictionary. And that's then inserted into my database. And I still also print it to the console. And with that, if I now run this script again and I try to read in all PDFs, I still process them like before and they're still sent to OpenAI. And I still get back the same result as before, so the data is extracted correctly. But now I have a bit of a easier time writing that code because a lot of work is done for me behind the scenes. But again, that's not necessarily available in all programming languages and also not with all providers. So knowing what happens behind the scenes is always important, which is why I showed it to you in the last lecture. Now, just to confirm that it was inserted into the database, let's have a look, and that's looking good. And that's how you can deal with structured outputs in your AI workflows and agents. I'm back in another multi-step workflow, or a multi-agentic system, again, just as you want to call it. In this workflow here, I start by loading an outline, which I added to this project, an outline I wrote, an outline for a new blog post that should be generated, because this workflow here is about generating a blog post. So that outline file gets loaded, or the outline from that file here gets loaded. Then I call generate article draft, which does what the name implies. If we take a look at it, we see that in there, I actually also load some example posts, which are stored here in this example posts folder. And these are just old blog posts I wrote in the past, a bunch of markdown files. And then these examples are merged with the outline in the end into one prompt where I instruct the AI to write a detailed blog post based on the outline by taking into account those example posts, but that it should only use the language, tone, style, and so on of these example posts, and then return the blog post in raw markdown format. Now, that's nothing new. You saw examples for that in the past in this course already. The only more or less new thing here is that I also have an instruction regarding the output format I want, because here I don't want structured data. I want plain text instead, but I want that plain text to use markdown formatting. And that's what I'm saying here, because I want to get a markdown file in the end. So that's just some extra instruction I added here. Now we'll skip this feedback part here for now. That will become important soon. For the moment, the only other interesting thing here is that I'm actually sending a more complex input to the model, to the GPT-4o model in my case here, because I'm actually sending two messages. And I mentioned before in this course that input can be a single prompt, which is what you typically saw throughout this section, but it can actually also instead be a chat history, which is important if you want to preserve past messages, for example. Now here I'm not sending past messages, but instead I'm using this history format, if you want to call it like this, to set a system message, a developer message. Now, in the past, this was called a system message, and for many other AI providers, it still is. In lots of documentation articles and blog posts, you'll find the term system message. But OpenAI moved to calling this a developer message with their new responses API. You can actually set both role system or role developer. And the role is important because that tells the model who's sending this message. If it's the user or if it's some general instruction that sits above all other instructions, so to say. Now, you don't have to set such a system message. We didn't do it thus far in this section, but it can make sense to set one, especially if you plan on managing a longer chat history, which I actually don't do here, but nonetheless, you can outsource your general instructions into such a system message. We could have also merged it into the user message though. For this use case, it's totally up to you, but I want to show you this pattern because of course it can make your overall prompt and workflow a bit cleaner if you put your general instructions into such a developer message. But other than that, I just send the general instructions and then the user message, which is my enhanced prompt here, which includes the outline, the example posts, and then these post-specific instructions. So that's that. And then I get back some generated text. Now here I got some code for cleaning that received output because it is possible that besides my instruction to return raw markdown, that the AI model actually sends me back a text that has the markdown code block wrapping thing here around my text. And I'm simply checking whether the text I got back has this at the beginning, which I don't want. I really want just the markdown code, no wrapping code like this. So I check if that exists, and if that's the case, I remove it manually with this code. Otherwise, I don't do anything. So that's just something to also be aware of. You can take a look at the output you're getting back, and you can do some extra cleaning if needed, because it's your code after all. You own it. And then I return that generated blog post, which now hopefully is in raw markdown format. Now back in this main function, I then got this blog post draft in Markdown format, and then I generate an image. And that's of course also something new. So thus far in this section, we only dealt with generating text, and that is a common task because you are dealing with lots of large language models which are all about generating text. But of course, there also are many AI tools that allow you to generate images. For example, OpenAI. They do not just offer endpoints for generating text with various AI models. Instead, they also support generating images. They actually also support analyzing images, so you could send images to their API to have the AI model have a look at them. And you can take a look at the official documentation to see how that would work. You would send a message that actually has a multi-part content where you can combine text and then an image. But here I'm looking to generate an image. And for that, again, you have different options. You can use this create endpoint, which we've been using all the time now, to send a prompt that describes your image, and then add this tools instruction where you tell the AI to use a tool called image generation, which is one of the default tools available to the GPT models through the OpenAI API. So that's one way of triggering image generation. Now, this approach here is especially useful if you plan on going back and forth, if you plan on maybe building your own chat application where users can refine images over time and where you maybe don't just want to send a single prompt like this, but where you maybe want to include a growing chat history. By the way, managing history and memory is also something we'll get back to in this course. If you just want to generate one single image based on one prompt, you could use this approach, but you can also take a look at their image generation guide and then use the image API, which they recommend, at least at the point of time where I'm recording this, if you only need to generate or edit a single image, which is what I want to do here because I only want to generate a single thumbnail. So in that case, they recommend that we use the image API. And of course, that may be different for other providers. This is just the example for OpenAI. And therefore, if I click on this image API, I now finally get some instructions on how to do that. Because now I can actually target client.images instead of client.responses.generate to tell OpenAI which image model I want to use. And at the point of time where I'm recording this, GPT Image 1 is the latest, best model they're offering. Then you would include your prompt that describes the image. You would set the number of images you want to get back. You can define the size, though you should take a look at their documentation because only certain sizes are supported. And you can also tweak some other settings. You could request a certain quality. The default is auto though, so OpenAI will decide based on your prompt which image quality it will generate. You can request different output formats, PNG, JPEG, or WebP, and also control other settings. Now, what's important is that at the point of time where I'm recording this, you must have a verified account in order to generate images. So in your organization settings, you must make sure that you are verified. Otherwise, you can't use these image generation endpoints. You need to go through that verification process in order to do so. But with that out of the way, you can generate images, and that's what I'm doing here in this generate thumbnail step. There, I'm using exactly that API I just showed you, the GPT Image 1 model, with my prompt where I include the entire article that was generated, and I tell the AI that it should generate a fitting thumbnail for this article. I want one image, and I want a JPEG image in this format, and then I get back that image as a base 64 encoded string, and I convert that to some raw bytes, which then are returned by that generate thumbnail function. And then it's these raw bytes that are actually getting stored in an image file next to my outline. I also store the blog post next to that outline then. And therefore, we can now take a look at that. I can now run this file, and as an input to this command, I should point at the outline file I prepared. So new post outline text, and it'll now go ahead, generate that article draft, and then also hopefully generate a thumbnail and save all next to my outline.txt file. And that's then an example for a multi-step workflow again that has some special tweaks and adjustments, and that's also including image generation. So the workflow did finish for me here. And let's take a look at the markdown file. Here we can see it also generated this metadata and then wrote this article, which looks quite good, I'd say. And it also generated this image, which also isn't too bad. Now, I will of course say that you always wanna carefully evaluate those AI-generated results. You can use the generated article here as a starting point. You can, of course, also publish it as is, but for example, here you can already see the date makes no sense at all. So you want to carefully evaluate it, not just the date, but the overall article, and tweak it. But of course, you can still save a lot of time if the AI gets you started with it, and you then just put some final touches on it. And that's therefore another example for a multi-step workflow that actually includes some more advanced settings and steps. Now, when building workflows, no matter if you're using AI or not, and therefore also when you're building AI agents, it's likely that not all steps need to run one after another, or maybe not all steps should run one after another. And thus far in this course, that's essentially the only case we had, right? We ran all our steps in sequence, sequential, which means one step after another. And we did that because many of our steps did depend on each other. And if step B depends on step A, it of course needs to run after step A. The last workflow I showed you, where we generated a blog post with an image, was a perfect example for that. We ran all these steps in sequence, and there's nothing wrong with that. For many workflows, that's exactly what you need, like for this workflow. But there also are workflows where you can run tasks or steps in parallel, which means side by side at the same time, essentially. And you would do that, or you could do that, if steps don't depend on each other, and it's especially useful if steps maybe take a bit longer. Because if you have step A, and that step takes quite some time, and step B doesn't depend on it, well, then it might make sense to run steps A and B in parallel so that step B doesn't have to wait for step A to finish just to get started. And I'll show you an example for that in just a second. You can also run steps conditionally, which means you would have two steps, for example, that depend on each other. So step B may depend on the result of step A, and step B therefore will run conditionally depending on what the result of step A was, and it may be skipped depending on that result. And I'll show you an example for that as well in just a second. And you can also repeat steps, so run them multiple times. That might make sense if you want to refine a result over time, if you gather feedback, or if you're building a chat application where you want to allow the user to ask follow-up questions. But actually, I'll show you examples for all four categories in the next lecture. So managing the control flow of your workflows and agents is important. That's why I prepared an adjusted example of that blog post generator, and as always, you find that attached, of course. Now, in this example, I'm still generating an article draft, but I'm then doing a bit more than just generating that draft and generating a thumbnail image. Instead, as you can already see here, I'm in a loop. an infinite loop by default, though I have an exit condition, no worries. In that loop, I keep on generating article drafts, but I no longer use just the outline as input. Instead, I also feed an existing draft, if it exists, as an argument to generate article draft, and some feedback, if it exists. Though initially, both does not exist. I don't have an initial blog post draft, and I don't have any evaluation result when that loop here runs for the first time. Still, this is already an example for some repeated task. Generating an article draft is repeated because it's inside of a loop. But of course, to make that more useful, I therefore need to gather some feedback, and that's what evaluate article draft does, which runs after generate article draft. So in sequence, it's sequential. And it's sequential because evaluate article draft, of course, depends on the result of generate article draft. It depends on that blog post draft. I feed that to evaluate article draft, and in that function, I then actually use OpenAI again, with some system instruction, some developer instruction here, and then my actual prompt where I tell it to evaluate the following blog post draft, feeding that draft into the prompt, and where I request the feedback as JSON, and I also request structured output by setting that text format parameter and by using this parse method on this responses API. So I'm picking up what you learned about requesting structured outputs here because I want to get some structured output which has this shape. I want to get a JSON object which has a needs improvement field, which is a Boolean, so true or false. And I want to get some feedback, which is a string, which should be the feedback generated by this evaluation step here, by this evaluation model in written form. That's what evaluate article draft returns, such an evaluation object. And that is then picked up in my main function here, and I then have a condition to execute some steps conditionally, implicitly at least. Because this condition is one of my two exit conditions for this loop. I keep on going if we need improvement, or put in other words, if we don't need improvement, if the evaluation step decided that the draft is good, I break out of the loop, I stop the loop, I stop repeating these steps. But if I do need improvement, if the evaluation step did decide that improvement is needed, I keep on going. And therefore, these steps are not just repeated, they're also conditional because they depend on this condition, and they will be repeated until this condition here is met. My other condition is that I only retry this for at most 3 times so that I don't have an infinite loop. I don't want that because I don't want to keep on paying for more and more drafts. But up to 3 times, I will keep on repeating draft generation and evaluations. And then once we make it out of this loop, once we have a draft the model is happy with, the evaluation model that is, once that's the case, I run something in parallel here using Python's concurrent futures feature, which allows for running tasks in parallel. Of course, different programming languages have different approaches for this problem of running code in parallel. This is one solution you could implement with Python, using such a thread pool executor. And what I am running in parallel here is my thumbnail generation and a LinkedIn post generation, which we didn't have in the previous example. Now, this generate LinkedIn post function here takes some example LinkedIn posts, which I have in this folder. These are just some example LinkedIn posts I wrote in the past. And then based on these posts, I ask the model to generate a new post. Again, having such a developer instruction here, feeding in my article in the user prompt, then feeding in my example LinkedIn posts, and requesting that it only uses the language, tone, and style of these posts, of these example posts, to generate a new post based on this article and these example posts. That's what generate LinkedIn posts does. And this is nothing new, but what is new is that I am running it in parallel with the thumbnail generation. And I'm doing that because generate LinkedIn post does not depend on the result of the generate thumbnail function, and vice versa. But generate thumbnail will take quite some time. So only starting the LinkedIn post generation once the thumbnail generation is done doesn't make a lot of sense. And it also doesn't make a lot of sense to wait with the thumbnail generation until the LinkedIn post generation is done. You could do it, but we can also speed things up by running this in parallel. And that is what I'm doing here. Now the next code line, this one here, will only execute once both tasks are done here, but since I start them in parallel, they will be done quicker than if I would run them one after another. Well, and then once everything is done, I just save my image, save my LinkedIn post, and save the actual blog post article. And therefore, if I now run this, and I now generate a new post based on my AI workflows versus agents outline here, we should see that hopefully this all runs the way I just described it. We start by generating the article draft, which of course takes a short while. Then thereafter, the evaluator should kick in. So now it's evaluating that article draft. And now it depends on the result of this evaluation. If it decides that improvement is needed, which it does here, needs improvement is true, it will actually generate an updated article draft based on the old draft and that feedback, that written feedback. So that's a good example. Now I got the updated draft and it will evaluate that updated draft again because we're still in that loop. And it again decided that it needs feedback. And again, here the written feedback is. So now it's going through another loop of generating an updated article draft, and we'll see if the evaluator is now happy with it. So here's the updated draft yet again, but still not happy. And by the way, I ran this before and it was happy on first try. So it's not always going through all possible evaluation steps, but here it is. It keeps on evaluating and keeps on providing feedback. So now I got another updated version of this article. And now it again actually wanted improvement, but we reached the max amount of cycles. So we stopped and now the thumbnail and LinkedIn post are being generated in parallel here, just as I explained it, to save some time. It'll still take some time, of course, but at least both tasks were started in parallel. So here we go. It is now done. And now I got an article in Markdown format. I got my LinkedIn post based on that article, and I got my thumbnail, which I could use for that article and also for the LinkedIn post if I wanted to, of course. Managing the control flow of workflows is important. What's also important is to sometimes add a human in the loop. Because not all AI workflows or agents should run fully automatically. Or put in other words, just because you're building an AI workflow or agent does not mean that you need to blindly trust all its decisions and let it do its thing totally on its own. Of course, you can build workflows or agents that are 100% automated, which means that once the workflow started, it runs and finishes on its own. Maybe some initial input is required. We saw some examples for that throughout this section, but thereafter you can lean back, relax, and you'll get a result at some point. And for many workflows, this is ideal. For example, that blog post generation workflow I just showed you. There we just start the workflow with some input, and thereafter no further input by us is required. And we can be perfectly happy with such a workflow, and that might be exactly what we want. But we can also add a human in the loop, and that may actually make a lot of sense depending on what your workflow or agent is doing. And human in the loop simply means that during execution, a workflow may require additional input or confirmation by the user. So not just initially, but also maybe sometime during the execution. possibly also multiple times. Again, it's your code, your workflow. You decide how it works and when input is required and when it isn't. For example, if you're building a workflow that automatically posts a suggested LinkedIn post to LinkedIn, you might want to add a step where you can check the suggested post and deny posting it if you're not happy with it. Or going back to this blog post generation example here, this is the same workflow as before, but I did now add a human in the loop step to it. And I added it because it's my workflow. It's my decision where I want user input and where I don't want user input. If you're building your workflow, you decide at which point, if at all, you want extra user input. Of course, this workflow worked fine without the input, but here I want to provide the user with an opportunity to share their own feedback on that article, to override the decision made by this evaluation step, essentially. And here I decided to give the user 3 options. Again, because it's my workflow, that's my decision. I decided to give the user 3 options. They can just hit enter, which means they will not provide their own feedback. Instead, they'll just accept the feedback generated by this evaluation step as it is. If this step decided that no further improvement is needed, the workflow will continue like before. It will exit out of the loop and the next steps will start. If the evaluation step did decide that improvement is needed, it'll go ahead and regenerate that article. So if the user hits enter, everything will work just as before without that human feedback step here. But that changes if the user enters the word accept. Because if the user does this, then we accept the article as is and we override any suggested changes. So even if this evaluation step decided that further improvement is needed, if the user enters accept, we discard this and we exit out of the loop and accept the article draft as it is. And the last option is that the user enters their own feedback, which also overrides the evaluation step result, because now we always request another iteration, we request a new draft, and we override whatever this evaluation step gave us. And here's the actual logic for implementing this. I'm checking whether the user entered accept, in which case we always set needs improvement to false, even if it was true before, which means we'll always make it out of this loop. We'll always continue with the next steps thereafter. If that's not met, we check if the user entered any feedback. So if they submitted a non-empty message, in that case, we also override the evaluation result and we always set it to true and we take that user feedback as a feedback for the next iteration cycle, for the next draft version. And if the user enters nothing, then neither of these conditions is met and the workflow continued as it was before. Now here for me, it will still stop after 3 cycles, even if the user did enter extra feedback. Of course, you could adjust the loop to make sure that if the user entered their own feedback, this condition here doesn't count. For example, if you adjusted it like this, you would make sure that the loop is only stopped if we have more than 3 cycles and we don't have any user feedback. If we do have user feedback, we'll continue even if we're above those 3 cycles. But that's something that's totally up to you. And with that, I can, of course, again, run this project here, this workflow, based on my AI workflows versus agents outline. And it will now go ahead and again generate a new article draft, of course. And then once that's done, it will again create this automated evaluation. That doesn't change, but thereafter, I'll get an opportunity to provide my own feedback. So here, the automated evaluation step actually did decide that further improvement is needed, and this is the AI-generated feedback. But now I have a chance of hitting enter to accept this decision by the evaluation model. Enter accept to instead accept the article, or enter my own feedback like should be shorter. Or of course I could also enter more. Here, I actually want to accept the article as it is, so I'll enter the word accept, and I overwrite the decision by this evaluation step, and therefore we now continue with thumbnail generation and LinkedIn post generation. And that's therefore an example for a human-in-the-loop step in this example workflow. Of course, you can also integrate third-party services into your workflows or expose them to your agents as tools, and we'll get back to agents and build them in detail in the next course section. But what do I mean with that? Well, not all your workflows and steps need to run locally on your machine and just use your own internal resources or publicly available resources. You can build such internal workflows, if you want to call them like this. So workflows that do only access your file system, send HTTP requests to public websites, and so on. But that might not always be what you need. It is what we did thus far. All the workflows I showed you worked without using any external third-party services. But you can also tap into such services in your workflows. You can, for example, send Slack notifications from inside your workflows or check emails from inside your workflows. You can use external services. And of course, depending on which kind of workflow you're building, doing something like that might make a lot of sense. Now, when working with external services, with external APIs, you will typically need to authenticate with them. Because if you're, for example, sharing a post on LinkedIn, you of course need to prove that you have access to the account for which you want to share the post. So those APIs will typically require you to authenticate in order to grant you that access. It also often makes sense to add an extra human-in-the-loop step to avoid unwanted results. If your workflow automatically publishes a post on LinkedIn, you might want to add a step that ensures that you're not publishing anything you don't want to publish. Now, when it comes to interacting with third-party services, like for example the LinkedIn API, you always need to visit their documentation because all these services have different APIs that require different forms of authentication and that expose different endpoints. There is no one single solution that would work for all these services. So if you, for example, want to share a post on LinkedIn, you should visit the LinkedIn Posts API. If it's a text-only post, you can dive into this documentation. And you can see which kind of request you would need to send to their API to create a post programmatically. As mentioned, you will typically need to authenticate and you'll need to add some token that's issued by them to your request to prove that the request is coming from an authenticated entity. And you therefore also need to check their documentation to learn how to authenticate with them. For example, here for LinkedIn, you could go to their Quick Start guide, and there you will learn how you can apply for API access. So that's one example. In my workflow here, I instead decided to send a Slack notification, though. And for that, I added a new function, send Slack notification, which takes the message as an input, which then sends a request to Slack according to their documentation. So just like LinkedIn, they have a documentation page where they explain how you can send messages programmatically. And again, you need to request access. For that, you need to go to their app management page and then there register a new app. In this case, I just created a little demo app. Then you need to go to OAuth and permissions. And then there, under scopes, you need to add at least the chat write scope. This will allow this app, this Slack app, to send messages to chats it has been added to. Once you did that, you will need to install this app into your Slack workspace. And once you did that, you'll get a token. This token has then been added to this .env file by me here. And it's this token that I'm also referencing here. And with all that out of the way, I can then send a message by specifying the text and the channel ID to which this message should be sent. For that, here on Slack, I created a brand new channel, and there I edited this channel and made sure that under integrations, I added this demo app so that this app has access to this channel. Once I did that, I took a look at the channel details, and there at the bottom, I find the channel ID, which I copied. And that's then this channel ID, which of course also will be gone when you are viewing this. And in Slack's case, that's already all. Then I just check whether everything worked or not, and that should do the trick. With that, I'm sending a Slack notification when that overall workflow is done. So if I now again start this one more time, and it again goes through article generation, through the evaluation steps, allows me to enter feedback, and then also through thumbnail generations on. Once all that finished, it should send me a notification to this channel. So here I decided to just accept the post as it is, without providing further feedback and without requesting more changes. And here we go. That's this message sent by this Slack app through our application here. So through this code I just showed you. And that's therefore one example for integrating a third-party service, Slack in this case, into your workflow. And of course, your imagination is the limit here. You can reach out to any service and do whatever you want. You'll just have to dive into their docs because that's the place where you learn how to authenticate and how to structure your requests to their APIs. So now that we got this solid foundation about building AI workflows, we're ready to finally start building AI agents and also agentic systems. Though, as I already mentioned in the previous section, you could already call some of the workflows we built there agentic systems, because some people would call each step we had in there an agent, since it was a task fulfilled with help of an LLM. But we'll get back to this in this section. Because in this section here, we'll explore in depth how to build agents. And with that, I also mean fully autonomous agents. Therefore, we'll take a look at how large language models do and do not use tools. So how we can build agents by exposing tools to large language models. We'll explore how we can build pretty generic, universal agents, and how we can build more specialized agents and which approach might be better in certain situations. We'll learn how we can connect multiple agents and build an agentic system. And we'll also dive into memory management. And with that, I don't mean the memory of your computer, but instead short and long-term memory that can be made available to agents to make sure that they're able to remember things. Again, plenty of things to cover. Let's dive in. In order to build AI agents, and with that I mean agents as defined by me earlier in the course, that act autonomously, that create a plan on their own, and that then execute that plan by using tools, if you want to build such AI agents, you of course need to understand how you can expose tools to a large language model, because it will be a large language model that powers such an agent. And what's extremely important to understand here is that the large language model itself will not use any tool. It will not execute any code. And I know that it can seem like it would directly execute some code. It looks like a smart system that's able to execute code on its own, right? But that's not what's happening. Large language models are just spitting out tokens. That never changes. But you can use this token generation mechanism to have it request a tool use, and that's what's actually going to happen. So you have a large language model that's running inside of an AI application. It's always like this. For example, ChatGPT is such an AI application that uses a large language model inside. The workflows we took a look at in the last course section are AI applications that use large language models in parts of this application. And AI agents would be another example for AI applications. And the idea is always that the application uses a large language model, but then does a lot of things in addition to create that overall AI experience. For example, an application like ChatGPT also manages a chat history, and that history is then sent to the model with every new message to give it the entire history to work on. It's also that AI application that would define tools that should be available to the large language model, so to say. And these tools are simply functions in the code, written by the developers that wrote the AI application. And we will write such functions, such tools ourselves in the next lectures to see how that actually works. It's then a description of these functions that's inserted into the prompts that are sent to the large language model to make the model aware of the functions, of the tools it can request. Because again, it can't execute them itself, it's just a token generator, but of course it can generate tokens that describe an intended tool use. And for that, you could add an instruction like this to your prompts, where you tell the model in the end that if it wants to use the web search tool, it should output web search : and then the search term it wants to use. Of course, that may seem like the large language model then is able to think about that and request it if it makes sense, but in the end, all this is doing is it's increasing the likelihood of tokens being generated that describe this web search tool use in this way if the rest of the prompt that reaches the large language model, which may contain a message sent by the user of the app, benefits from that tool use. But it's all just about token generation and about increasing the likelihood of the tool use description tokens being generated by the large language model, if you want to put it like this. So then, depending on the rest of the prompt, the large language model may indeed output web search : current president of the USA if the user, for example, asked for that current president. And because of its training and its fine-tuning and the overall prompt engineering, the large language model may output tokens that form this text in the end: web search : current president of the USA. Now, the idea is not to show this text to the user who sent the original message, of course, because that's not an answer to their question. Instead, the AI application that's talking to the large language model would capture that result and would take a look at it. And it would look at this result and check whether a tool use is requested. And it knows how a tool use request looks like because it was also this AI application, or the developers of this application to be precise, that added these instructions on how tools should be requested to the prompts. So the application would simply check whether one of these instructions was output by the large language model. And if such a tool request is detected, then it's the AI application that invokes the actual tool. So that invokes the actual function, which is also part of the application. And it would forward that search term to that function. And then, of course, it would be the result of that function call that would be passed back into the chat history, back into a prompt that's then sent to the large language model. So the large language model would then receive an updated chat history that includes the result of this function execution, of this tool execution, you could say. And then the large language model generates the final output. That's how tool use works. And if that looks confusing, no worries, we'll build it from scratch, step by step, so that you understand in detail how that all works, and so that you're able to build your own tool-aware agents in the future. So, in order to fully understand how large language models use tools, let's build a simple agent that's able to use one tool. And for that, I'm in a brand new project. I again created it with UV init. I got my .env file, which contains an OpenAI API key. I got a pretty empty main.py file, and you can of course create any Python project you want with any tool you want if you want to follow along. I did add python.env and OpenAI, these two packages, python.env to load the environment variables specified in the .env file into the actual environment to make them available here, and OpenAI, of course, to be able to use, well, OpenAI. Because I want to import OpenAI and just like before, create a new client by instantiating OpenAI like this. You could then set your API key, but if your API key actually is named OpenAI API key, you don't need to do that because it will automatically look for that. And therefore, we're now ready to build our first tool-aware agent, if you want to call it like this. For this, I'll first start by creating a tool, and I'll name that tool getTemperature, and it's just a dummy tool for now. It's called getTemperature, and I expect to get the city for which I want to get the temperature as an input. And then this should return a floating point number. And for now, I'll just return a dummy value, so these suggestions by Copilot make sense. And that's therefore all this will do for now. It's not a real helpful function, it's just a dummy function, but of course you could imagine that in this function we might be reaching out to some weather API and we might be looking for the actual temperature for a certain city. For this demo, I'll just hard code a fixed temperature. The idea now is to now talk to a large language model and get it to request the execution of this function if a user asks for the temperature in a certain city, but not if the user asks for something else. So therefore, in the main function, I will get some user input, and I don't want to get just a city name, but instead any question, because here I want to build a versatile AI application, a versatile agent, if you want to call it like this, who's able to help with all kinds of things. And I want to give it the temperature tool so that it can, but doesn't have to use that tool if the user asks a question that is about the temperature in a certain city. But the user should be allowed to ask any kind of question. And that's already an important difference to all the workflows we took a look at in the previous section, because there we had workflows that focused on a specific problem. And therefore we had step-by-step tasks that needed to be executed, and we were looking for a specific input because we also knew that we would be executing those workflows and we knew how to execute them and which input is required. Here, instead, we could be building a more versatile application that we also want to expose to other users, a customer service agent or something like this. So that's one important difference. Now the goal is to send this as a prompt to the AI model. And for that, I'll use client responses create, just as we did it before. And for the model, we can use various models, of course. I will use GPT-4o again, also because it's relatively cheap. And for the input, I want to send the user input. I want to forward the prompt sent by the user to keep things simple right now. And of course, we'll get back a response here. And that response will contain some output text, which is the reply by the model. And then I'll output that reply. Now, at the moment, there is no tool use in there. This model doesn't know anything about this function. And of course, therefore, if I execute this code, if I run this file, I can ask my question and ask, what's the temperature in Munich today? But as a result, I don't know what I'll get. Yeah, I'll get the information that it doesn't know that, which is better than hallucinating something. But it would be even better if it had access to this function, right? And that's what we'll do next. And for this, as I showed you on the slide, we can try engineering a special prompt. So we can add a prompt which builds up on that user prompt. And in there, we could say something like, you are a helpful assistant, answer the user's question based on the following context. No, answer the user's question in a friendly way. You can also use tools if you feel like they help you provide a better answer. And then I want to list my tools, and here I'll describe this function, get temperature, get the current temperature for a given city. And I'll say, if you want to use one of these tools, and at the moment it's of course just one, you should output the tool name and its arguments in the following form. And then I have an example. For example, get temperature New York. And actually, I don't want that format, which was suggested to me here. I instead want tool name, colon, arg1, arg2, and so on. And the updated example then looks like this. With that in mind, answer the user's question. And then, I like those delimiters, user question. If you request a tool, please output only the tool call as described above and nothing else. And this may or may not work. It's not the best way of requesting tool use with OpenAI, but it is a way that in theory should work with all large language models because it is just about increasing the likelihood of the right tokens being generated. So therefore, let's give this a try. Let's send this prompt to OpenAI, to the GPT-4o model in my case here. So if I ask what's the temperature in Munich, then I indeed get back the response I wanted. Get temperature Munich. And now, of course, since I'm building this application, I could check if reply is equal to, or I should say starts with, get temperature, then I want to get my argument, or my arg, by splitting the reply at the colon, and I know that the part after the colon will be the argument, and I call strip to remove that white space, so that I get just the name of the city. And then I get the temperature by executing this get temperature function and by passing this argument as a parameter to it. And get temperature is, of course, my function. So as you can see, it's me, it's my code that executes this function. It's not the large language model. As explained before, it's our code. The large language model just requests the use of this tool. Now, of course, I could then output this temperature, but I still want to get a reply that's generated by the model. So what I'll do instead is, if a tool use was requested, I'll request another reply by the model. And we could do this in a more elegant way. Here, I'll keep it very simple, deliberately, to show you step by step what's working. So I'm sending another request to OpenAI, but now I need an updated prompt. I need an updated prompt that takes this temperature information into account. So I can build my updated prompt here and say, you are a helpful assistant, answer the user's question in a friendly way. And now I could pick up that user question. Here's the user's question, like this. You requested to use the get temperature tool for the city arg. Here's the result of executing that tool or of using that tool. The current temperature in arg is temperature. So I put the result of calling that function into this updated prompt. And now it's this updated prompt that's sent to the model. Now there would be other ways of doing that. We could also manage a chat history and add this as a new message in the chat history. But to keep things simple, I'll do it like this. And now we'll get an updated reply, and then I output that reply. By the way, I also want to output a reply if we don't make it into this if block. So if the tool did not request a tool use, so I will add an else block, and in that case, print the old reply. So this reply, so that we output a reply either way, no matter if a tool use was requested or not. And with this updated code here, if I again run this and I ask what's the temperature in Munich, it should now call that function behind the scenes and then output that it's 20 degrees, because that's what my get temperature function always returns. And that proves that it works. Now, to really prove that, I'll also add a print statement here and say fetching temperature for city so that we can see when that tool gets called. And with that done, if I run this again and I ask what's the temperature in Berlin, We should soon see that the tool is being executed. Here we go. And then we get the updated response. Now, if I ask for something else, like, what can you do for me? We should see that the function does not get executed. Here we get a normal response, though it does inform us that it can get the temperature for a city, because of course the information that it can request this tool use is in its initial prompt. So it's pretty smart that it tells us that it could do that for us. But the function was not invoked here because our prompt did have nothing in it that would have increased the likelihood of the model to request this tool use. And that's therefore how large language models use tools. Now that's a very verbose way, but that's important to understand how it works. Now I'll show you a more elegant way you can use when working with OpenAI and also with many other providers. Now you can implement tool use and build agents as shown in the previous lecture. The advantage of this approach is that it should work with all large language models because the prompts didn't contain anything OpenAI specific. You could have sent them to any models. But exposing tools to large language models and describing tools that may be used by these models is such a common use case, such a common scenario that many AI providers actually have built-in support for it. Like, for example, OpenAI. They are calling it function calling, but chances are high that if you're going through the docs of some other provider, you'll also find official tool support. In case of OpenAI, you will actually also find a tools section in their docs, but this actually refers to tools that are running on OpenAI's servers. So tools, functions written by the OpenAI developers. This can also be useful because it, for example, allows you to request web search or expose a web search tool to the large language model that you don't have to write yourself, which can be pretty good because web search is complex, but it's not the focus of this course. Instead, we will focus on building our own tools. And that takes us back to this function calling topic, because that's simply the term OpenAI is using for allowing you to expose tools, which are just functions, to a large language model. And to do that, their docs show us that you should expose a tools argument, or that you should pass a tools argument to this create method when using the Python SDK, and there the responses API. If you are using some other programming language, you can of course also just send an HTTP request to the API endpoint and then just include a tools property in the request body. So of course you can use this feature from any programming language. Now the value for this tools parameter then actually should be a list of tool descriptions, a list of function descriptions, which must have this shape. And if that looks familiar from the structured output lecture, that's no coincidence because the idea is kind of the same. With structured outputs, we tried to describe the data format we wanted the LLM to generate. With this function calling feature here, we're trying to describe the functions it may request from us, so the functions it requests to call. And therefore, this is the shape of this definition you have to use in your code. And that is how you can define different functions and their parameters that may be invoked by the tool, or that may be requested to be invoked by the tool, I should say. If you do provide such a tools parameter, then you will actually get back an output that may look like this, if the model decides to call a tool. Of course, it might not always do that, depending on the prompt that was sent to it by the user. That prompt, by the way, then no longer needs to contain any information about the tools. The OpenAI API will handle that behind the scenes for you when you're using this tools feature. But if the model then decides to use a tool, it will send back an output which contains one or more items. And the first item then would be of type function call, containing the name of the tool, the name of the function it wants to call, and the values for the arguments. And of course, the name and the argument shape here depends on the structure you defined. That's the idea. And you can build pretty complex workflows here because the OpenAI API and their models actually also support multiple tool calls in one single request. So the model could request multiple tool calls. You could get back a response which requests multiple tool calls. And you can go through the official documentation to learn more about that if you want to dive deeper here. This course is not an OpenAI course though, I'm just using it for my examples. Instead, I want to focus on how you can generally implement tool call. And for that, we'll for now focus on one tool being called at a time. And therefore, I prepared an updated version of this demo program we built in the last lecture of this first demo agent. And you find that updated main.py file attached. In there, I still have the getTemperature function, but the rest of the code changed. I do, for example, now have a tools list, which contains one tool description in that shape we saw here in the OpenAI documentation, because I'm talking to the OpenAI API here. So I got that. I also got the available functions dictionary here, which simply keeps track of all the functions I want to expose as tools, and I need that a little bit later in my code. But first things first. In the main function, I'm now working with a chat history, which I manage. This is optional, but it helps if you want to build a chatbot. And that is what I do here because I actually changed this program to have an infinite loop. There is a way of getting out of it though. The user can type exit, but other than that, we keep asking for more questions and we keep prompting the model. That's why I'm managing a chat history here, and I start with a developer message, which is a system message with some general instructions that should be followed by the tool. Then I append the user input to that chat history, and then I send that to the model. And here I also set up those tools. I make the model aware of the tools, so to say. Or the OpenAI Python SDK and API does that for me because I'm using this tools feature to be precise. I then take a look at the output I get back, at the first output, because as mentioned here, I'll only deal with one tool call at most. I append that output object to the chat history just to keep track of it, so that the model also knows what it replied in the past. And then I check whether the output type is maybe not a function call, which means the model did not request to call a function. It sent back a normal response instead. In that case, I simply output that response text and I continue with the loop, skipping these lines of code. Instead, we restart the loop asking for more input because I'm building a versatile agent, a versatile chatbot here, and a chatbot is just an AI agent in the end. And that chatbot, of course, can help with all kinds of questions, and not all questions require tool use. If we make it past this if check, though, we know that a tool call, a function call to be precise, was requested, and that's where execute tool call comes into play. That is a utility function I added here, which gets that output object that was returned by OpenAI, and that then extracts the name of the function and the arguments of the function the model gave me. So it extracts that information about that intended tool call the model provided to me. Then I check whether the requested function name is in my available functions, so if the model requested a function I want to support, just to make sure I'm not executing some function I don't want the model to request. And if the function that is requested by the model is supported, I try executing it. I get that function from my dictionary here, I execute it, I check whether that works and handle the exception if it doesn't, and I return the result of that tool call. And that's then what I'm using here, the tool output. I add that back into the chat history using this special type, which I know from the OpenAI documentation. And that's why it's important to dive into the documentation if you're building more advanced things with an AI model, with an AI provider, because they do offer all kinds of features. For example, here I can set the type to function call output. This is supported by OpenAI to give the model the information about the result of the intended tool call, because I also put that result into this message. And then I request a new response based on these updated messages, which includes that tool call result, and I output the final result I get back, the final response. Please note that here I no longer expose tools to the model, because in this app here, in this chat app, I don't want to support subsequent multi-step tool calls, instead just one tool call per user question, so to say. But that's then one way of implementing this in a relatively clean way. And therefore, of course, here, if I run this main file and I ask, what can you do for me? It should not execute this getTemperature function. I should not get any log regarding that. Instead, I get the default response, which is good. If I now ask, what's the temperature in Tokyo, then I should see that that function gets executed, and I then get a reply that takes the result of that tool call into account. And now I'll type exit to quit, and then here in this program I actually output the entire chat history so that we can see what was inside of it. Like that system message I set at the beginning, the initial user message, the initial response to the first user message, the subsequent messages, the tool call results, and so on. And that's how you could build, or how you could handle tool calls when using OpenAI, and in this case, the Python SDK. So we got started building agents, which in the end just means giving large language models indirect access to tools. At least if your definition of an AI agent also is an autonomous program that is able to perform work on its own with help of those tools. If you have a different definition, you maybe already saw agents in a previous section, because we there already built workflows that consisted of multiple agents that worked together. But for autonomous agents, we saw a first example in the previous lectures where we built agents, AI agents, by equipping large language models with tools, which in the end is the idea behind an agent according to this definition here. Now here's another more realistic example of such an AI agent. You find this updated main.py file attached, and also this database py file here. And this file, or these files, actually set up a customer service agent. Still a dummy agent, which of course is missing many functionalities, missing extensive testing or potential checks or guardrails you might want to add, but still a great example for a pretty versatile agent that is able to use multiple tools, not just one, and also multiple tools per question by the user, as you'll see in a second. Here I also got a dummy database, a dummy SQLite database that's running in this project, still the same project created with the UV tool I showed you before. And in there I'm creating some dummy tables, one for customers, one for orders. Every customer has a first name, a last name, and a PIN. And the PIN here will be stored as plain text in that database. You would not want to do that in production. You would want to hash it there, but to keep things simple, I'll store it as plain text here, as you'll see. I got a simple orders table, which has order IDs, customer IDs, a date for each order, and also a product name and an amount for every order. And then I clear these tables whenever I start this program to then repopulate them with some dummy data. And as mentioned, these are the plain text pins, which again, you wouldn't store as plain text in a production database. That's important. But for this demo, it's fine. And then in the main py file, I got a bunch of functions, a bunch of tools. Well, first I create that database, of course, but then I got a bunch of functions, a bunch of tools. Like the verify customer function, which takes the full customer name as an input and the PIN of the customer. And then we try to find that customer, and we use that information, whether we found the customer or not, to either confirm their existence and return the customer ID, or to return -1 if we did not find a customer for this combination. We got a get orders function, which takes a customer ID to retrieve all orders that belong to a customer. Check refund eligibility, which takes a customer ID and an order ID, and then queries the database and checks the date of an order and checks whether it's within the last 30 days to either return true or false, determining whether the customer may get a refund for a certain order or not. We have this issue refund function, which just prints something in the console. Of course, in reality, this function would trigger some refund process. We got a share feedback function, which does kind of the same. It just prints something, but in reality, that would be stored in some database. And then just as before, here I went for this approach where I register all functions that may be called by the large language model. And then here I have my tool definitions for the large language model. And again, these have the same shape as before. They in the end describe all these functions you saw up there. I still also get the same execute tool call function as before to have a flexible way of calling various tools. And then in the main function, I'm building the actual agent. I do that by setting a rather long system, a developer message, where I give the agent clear instructions on what they must not do, what they should do, how they should behave if they can't answer a certain question, and so on. And then I have an infinite loop, still with an exit condition if the user types exit, that allows the user to interact with this chatbot. I save each user message in that chat history so that the large language model always gets the entire history and knows everything about the ongoing interaction. And then here I got a new nested loop, which I have to limit the amount of tool calls per cycle to prevent infinite loops, in case the model should get into a cycle where it keeps on asking for more and more tool calls. I don't want it here, which is why I limit it at 5. So that in one single go, in one single cycle, for one single question by the user, it can't call more than 5 tools. That's my idea here. And then here I send the current chat history to the model. In this case, using GPT-4o, we could also try using a smarter model like o3 or something like this, but I will use 4o here also because it is rather cheap. But this is definitely a use case where you could consider using a more powerful model because we have quite a complex task here with many tools that may be called. So you definitely want to test different model versions if you were to build a bot like this for production. I also expose the tools to the API, to the model, of course. And then I take a look at the output. And I mentioned before that OpenAI can return multiple outputs per request. For example, it could return a message, a reply to the user, and at the same time request a tool call. And we'll see that in action here once I run this actually. That's why I loop through all the replies I got for this one single request. And I take a look at whether it's not a function call, in which case I output the text that I got back from the model. If it is a function call, on the other hand, I go ahead and try executing that function, and I append the result of that function call to my messages. And then here I have a little exit condition outside of this loop, but inside of that tool loop here, where I check if the last message we saved is not a dictionary, because all these messages, all these replies which I append here, which I get back from OpenAI, are actually not dictionaries. They are objects based on classes. So if I got such an object and the message type is message, so if I got back a regular message as the last reply by the model, then I know it's done doing tool calls for this cycle, which is why I then break out of this tool call loop back into the main loop where I allow the user to enter more information. And it's best if we just take a look at that in action. So I will run this main.py file, get the starting message here, and I'll say I want a refund. And now you will see that the model tells me that it can help me with that, but it needs my full name and my PIN. Now if I say something like, I don't know, it should not continue, because it should only be able to help me if I do verify, and it does that. So I'll say, sorry, my name is, and I'll take a look at my database here. And you see the customers I added, which you also, by the way, see in the database py file. These dummy customers, they're called Jane Smith, 5678 is her PIN, and John Doe with 1234. So my name is Jane Smith, 5678. 577. I enter a wrong pin here. It's a lowercase, but the function where I verify the identity is written such that casing shouldn't matter. So I have a wrong pin. So now you can see that tool was called, but correctly it identifies that this returned false. I was not verified. So I'll say, sorry, the pin is 5678. And I don't re-enter my name, but since all these messages are saved in the chat history, it recalls that my name was Jane Smith, and it is able to verify me. And it also then called another tool here, get orders. So that is multiple tool calls for one input from my side, where it retrieved all orders for my customer ID. And in my case, it found one order, which makes sense because for the orders that are being inserted here, this second customer, Jane Smith, only has one order, which is a keyboard for $75, which is exactly the information it's showing me here. By the way, you will get different replies when you're running this, most likely, because it is not deterministic. It's an AI model, it's generating tokens. But here, this all makes sense. So now it's asking me whether it should check if that's eligible for a refund, and I'll say, yes, please, I want this to be checked if I can refund it. So it goes ahead and calls check refund eligibility, and it tells me that it is eligible, which is correct. So I'll say, so please go ahead and refund. And now it calls issue refunds, gives me the confirmation message, and everything's fine. So now I'll exit here. That all worked just as it should. Now if I restart this and I ask like, what is the weather? It should tell me that this is not really something it can help me with. If I ask, what are John Doe's orders? It also shouldn't proceed with that unless I verify. So I'll verify with Jane and I'll say, sure, I'm Jane Smith. My pin is 5678. This should not get it to reveal anything about John. So it gives me my order history, which makes sense. That's good. It does not reveal anything about John. Now, you may be able to break this because, again, it is a dummy example still, but it is an example of a more capable AI agent, a pretty versatile AI agent that got plenty of tools to choose from. And ultimately, that is, of course, the idea behind building AI agents. When building AI agents or AI workflows, or actually when writing any kind of program, you can of course write the code you want. You can follow patterns you want. You can use design approaches you prefer. What you'll often see when working with AI agents, though, is that classes are being used, that object-oriented principles are being used, at least to some extent. Which is why I migrated this example from before, which was only using functions, which again is fine. But I still migrated it to a class-based approach to also show you how that could look like, in case you're interested in that. And for that, of course, attached you find an updated main.py file. The database py file did not change, but in the main.py file, I defined a tool class, and we'll take a look at it in a second, and then some specialized tool classes that extend this base tool class, and we'll dive into those in a second too. And you already might guess it, I defined an agent class, a base class, and then also a specialized agent class for this customer service agent. And the idea behind this class-based approach here, of course, is that you could easily add multiple tools or multiple agents and build up on those base classes so that you don't have to re-implement all the logic over and over again. And it's of course up to you how much logic you want to shift into the base class and how much logic you want to keep specific to a certain tool or agent. Now let's start with the tool base class. Let's start with exploring that and how such a class could look like. And here I decided that a tool in the end is just a function. So it should have a name, it should have a description, which is important for the AI model, for the large language model to evaluate whether a certain tool should be used or not. and it will have parameters. So I store that here. I have a getSchema method in the base class, since all tools need to be able to produce a description of themselves, so to say. They need to be able to produce such a schema because it is that schema that's being passed to the large language model in the end. So I dynamically generate this schema for every tool, and the logic for that is in the base class. And I just return a JSON schema as you saw it before, but now it's defined once and can then easily be adjusted or be called for different tools. And then I have an execute method which does not have any logic in the base class because, of course, the concrete logic for executing a tool is something that belongs into the specialized classes that extend the base class. Like this verify customer tool. In there, I start by having my constructor function here, and there I simply set all these parameters like the tool name, the description, and the parameters. So this description of the tool that will be important to the large language model. And then we have the concrete implementation of this execute class. And there you have the same logic you saw before for reaching out to a database or doing whatever a tool needs to do. And it's the same for all these tools. They're just now in this class shell. Now for the agent, it's kind of similar. I have a base agent class which stores information like which client is being used for interacting with the AI and which model I want to use. In this case, it's all focused on OpenAI, of course. I have my messages, so this short-term history I manage for each agent, that chat history in this case. I have my tools, because every agent kind of needs tools, or not every agent needs tools, but many agents do, so I want to be able to store that information about the tools. And then I have a register tool method, which simply adds a tool to this tools dictionary. I have a getToolsSchemas method, which calls getSchema, that method we just saw, which describes a tool for every registered tool, so that we get an overall list of tool schemas, which is the actual thing we'll need to pass to the large language model, a list of all tool descriptions. I have an execute tool call method, which in the end executes a tool, but also has those extra checks to see whether a tool exists in an agent, and so on. And then a run method, which is not implemented because, again, I decided that here for me, what exactly happens when an agent is executed can be very specific to the exact agent. Some agents might need to return structured output. Some agents might want to have a more complex interaction with the user. So I don't want to have the logic for that in the base class. Instead, that will go into the class that actually extends the base class, into the customer service agent, for example. So in that agent, I start by, of course, initializing the base class. I do that by setting the model I want to use. I then also set the initial prompt and register all tools. Set initial prompt simply adds one message to my messages list, which is that developer message, that system message. And register all tools does what the name implies. It goes through all the tools this specific agent should have access to by instantiating those specific tool classes. And then it calls register tool to pass those instances of those tool classes to register tool to make the agent aware of these tools. And then the run method contains the concrete logic, which again, for me is very specific to a concrete agent, and therefore I keep it here in the class that extends the base class instead of in the base class. But the logic is the same as before. If I run my program here, which does nothing else than instantiate the customer service agent and then run it, I can interact with it just like before. So if I say I want a refund, it should still ask me for my details, and it does. If I enter something wrong, like a wrong pin here, it should ask me for clarification, so I can say, sorry, the pin is 5678. And with that, it then hopefully goes ahead and gives me more information. Yeah, it found my keyboard order. So I can say, yes, I want a refund for that. So let's see what happens now. It's eligible. Yes, I want the refund. And it does that. So that still works the way it did before, but now using this class-based approach. And again, it's totally up to you whether you want to use an approach like this or not. It's your code after all, but some people would consider this cleaner, easier to extend, easier to implement with multiple agents, and that's why I wanted to show it to you. Also, because we will now move on to using multiple agents and connecting multiple agents. I'm back in yet another new project, which you of course also find attached. It's a main.py file and a database.py file. And I'll get back to that database in just a second. This project here is a very simple, basic web research tool. A tool which actually does not visit websites and extract content, but instead a tool that's all about creating a research plan and then having the AI perform web search based on that research plan and then return a summary of the research results, a summary of the links it found in its web search. And whilst this isn't a super complex program, a super complex application here, it is indeed an application that allows me to show you how you could build an application that takes advantage of multiple connected agents. Now, just as before, I'm working with a base tool class, which looks and works exactly as shown before. And I then have a couple of classes that use this tool class to build some concrete tools, and I'll get back to those in a second. I also still have my agent class, which also works the way it did before. And then I got a couple of specialized agents, and that's where things will get interesting now. Just like before, these agents can register tools. And for example, I have a research planner agent whose task is to create a research plan together with the user. So the user specifies a topic, and then the idea is that this agent goes back and forth with the user to refine the research plan or to create a refined research plan. And you'll see that in action in just a second. This agent also has access to some tools that allow the agent to store a research plan for future use or to retrieve an existing research plan, or actually all existing research plans, and delete research plans. And these are these tools I mentioned before. In these tools, I, in the end, just reach out to functions defined in this database PY file to keep this main.py file a bit leaner. In this database.py file, I'm again using a SQLite database, and I have very simple functions for initializing that database and creating a research plans table where every research plan has an ID, a short summary, and some details. And then I have these functions for adding or retrieving or deleting research plans. Pretty straightforward and deliberately kept simple for this demo. So these are the tools available to this research planner agent. I also got a system instruction here where I try to guide this agent and make it clear how this agent should work and how it should try to help the user. And then we have this run function. And again, I opted for a design where I don't have a lot of shared logic between agents. I have none of that actually. The base run function, the base run method is empty. Instead, my idea really is that I want to be able to build agents that are really different from each other, where every agent can do exactly what it needs to do and where I can fine-tune the logic for every agent, which is why every agent has its own very specialized run method. Like this research planner agent, which actually spins up a little chat. It has an infinite loop with some exit conditions, and in that chat, it tries to refine that research plan together with the user. asking for initial input, and the user can also insert exit to exit the entire program, or accept to accept a research plan and move on. We'll also see that in just a second. But if the user enters anything else, that input will be used to refine the research plan. And for that, I got a nested loop here, actually, to allow the agent to also use tools. Because, of course, the user also might have asked the agent to store the research plan or get existing research plans. So that's all in there, and that is kind of similar to what you saw before in the previous example. Ultimately, this agent here, which is using the GPT-4o model, because all my agents here do, also for cost reasons, this agent here will in the end produce a research plan. And that's also important. If the user types accept, the plan is to move on, and therefore I have some extra logic here that prompts the agent to actually produce a final version of the discussed research plan, so that it takes a look at the entire history, and based on what the user and the agent decided, it will produce one final research plan, one final description of how the research should be conducted. And then, and that is new, I return that research plan that was produced here. I return that here in that run method so that I can hand it off to some other agent. An alternative approach would be to spin up another agent in here, but I went for this return approach. Now, where am I returning it to? Well, that would be my main method, my main function here actually. It's here where I create that research planner agent, where I started, and then that's the research plan that is ultimately returned by agent run. Because that's how this agent works. Again, if you're writing your own code, you have full control over how things should behave and how you want to connect different things. And speaking of connecting things, the idea here, of course, is to have multiple agents that are working together and that are connected by passing data from one agent to another. So the result from this research planner agent should be passed to the web search agent. How am I doing that? Well, this web search agent also has a run method, but unlike the other run method, here we want an input. And that is that research plan that was created here. And again, that's just one way of doing it. You could also build your agent such that you can pass data to it through its constructor, or you use some dependency injection mechanism, or you store that data in some global variable to which all agents have access. This is entirely up to you. I went for this approach here. So what's this web search agent doing? This agent here has also a system prompt where I instructed that it will perform web search and that its main job is to derive meaningful web search queries and to also derive some web search result age restrictions, depending on the research plan. That's the idea. However, the run method of this agent looks totally different from what we saw in the research planner agent. Because again, I like to be flexible here. I want to be able to really tailor each agent for exactly the task it's meant to perform. This run method, for example, takes an input. As mentioned before, it takes the research plan as an input. And it also doesn't spin up a chat, because the job of this agent is not to have a conversation with the user. Instead, the job of this agent is to perform a certain task, which is deriving search terms and also performing that search. Therefore, this agent actually has no access to any tools. And therefore, you could, of course, question the fact whether it should be called an agent. At least if you recall my earlier definition of an AI agent. But as I also mentioned back then, there are simply different definitions, and many people would call a thing, an entity that's able to perform a certain task with help of AI, an AI agent too. So following that rationale, this is an agent here. If you want, you can of course also call it web search step or something like this, if you want to have a clear differentiation, but I don't think that is too important. Ultimately, the idea is that we build an AI-powered application, a workflow that may use true autonomous agents and then maybe specialized agents that are not autonomous. And how you define things is up to you. There is no fixed definition here. But that's important. This web search agent is not autonomous. It does not have any free will, so to say. The research planner to some degree was, because it can call the tools it wants depending on the prompts. It's a chat, an ongoing discussion, and therefore it's not exactly clear when the interaction with this agent will end and what exactly the output will be, if any tools will be called. That's all not clear. In case of the web search agent, it's very clear what's going to happen because it's a step-by-step process, as you saw it in the previous course section about workflows as well. Because this is just a little mini AI workflow within an agent in the end. And that is, of course, something you can absolutely do and you will typically do quite a bit. So what I'm doing here is I'm first getting this agent to derive a bunch of search terms based on that research plan and based on that system prompt, of course. And I do that using structured outputs using the OpenAI API here, because I'm using OpenAI everywhere in this program. I have my search config Pydantic class for that controls the format of the structured output I want. That I need a list of search terms, which is just a list of strings, and some information about the freshness. And this freshness is either a string, which is a time frame or two timestamps actually describing a period, or it's one of these strings here. And I'm using these specific strings because in this example, I'll be using the Brave Search API, which is a third-party web search provider which you can access through their API. And the nice thing about Brave Search is that you can get started with it for free. So you don't have to pay for them, you just have to create an account and then you can get started using them. And when using the Brave Search API, you can define a freshness, which is one of these values. And that's exactly what I'm reflecting in my code. So that's exactly what I have here. So that is what I want the AI model to produce based on the research plan. I then take a look at the search terms the model came up with, and I go through all the search terms it derived, and I send a request to this Brave Search API using my Brave API key, which you need. And you can get that if you sign up with them. As mentioned, you don't need to pay. So I'm sending a request to this third-party API using the freshness determined by the model and the search term determined by the model. I send that request, I get back my response, and then I parse the results from that response I got back. And the Brave Search actually returns a response object which can contain a lot of data. I'm only interested in the web and the news results here for this demo. And that's therefore what I access in my code. I take a look if we got some web results, some news results, and if we do, I dive into them and I simplify them. I just extract the search term that was used, the URL of that result, and that short description that's included in the response returned by the Brave API. And then I return those simplified results. So this web search agent performs the web search and then returns those results. That's the job of this agent. And again, if you call it an agent or not is totally up to you. So then I got my results, and I then hand those results to the summary report agent. Now, please note, I'm not visiting those results. You could add another agent that visits all these websites. Now, for some websites, that could be tricky. They might not load all the content initially. They might have bot detection. So you might need a more elaborate approach for visiting such a site and extracting content. And in the next lecture, a text lecture, I'll share some details on how you could try to tackle this problem. But here I'll just generate a report based on these raw search results, which of course don't contain a lot of information, but at least short descriptions for each search result. So I got the summary report agent for that, yet another agent which isn't really an agent because it doesn't have tools, it's not really autonomous, but again, you can call it whatever you want. It has a system prompt, And again, a customized run method, which takes these search results as an input and which then simply constructs another prompt asking the model to create a summary based on these search results, passing the search results as a JSON string into the prompt. And then I just extract that summary. I requested it in markdown format, but it's possible that the model included these code tags at the beginning and end. So I'm checking for that, removing them if necessary, and then I return the report. And that report is then simply saved in a file. So still not a super complex application, but a great example for multiple agents or semi-agents working together. And it also shows you how you can connect agents. Again, you can of course also connect them in other ways, but this would be one possible approach. And therefore now if I run this file, it all starts with the agent asking me for my research task. So I could say, I want a summary of core things that happened in the world of generative AI. And I send this to the model. And keep in mind, with this first agent here, we're having a conversation. It's a chat. So let's see what we get back. So this is the research plan suggested by the model. And I want to focus on just Google, Anthropic, OpenAI, Microsoft, and XAI. That's something I want to do. And let's focus on this year only, 2025. I shouldn't have to enter this year because in some of my system prompt, I actually inject the current date here to make sure that the model knows what the current date is, but still, it doesn't hurt. So let's see. Okay, now we got that revised plan, and let's say I want to save that for future use. Because maybe I want to do that same research again in 2026, or I want to build up on that plan in the future and refine it. So I can say, please save that plan, because keep in mind, this model has access to tools that allow it to save a plan, for example. So now it has been saved, and therefore now I will enter accept here to accept the plan as it is, and now it will produce that final version of the plan, and we'll move on to the next step, which is to derive search terms. So the next agent will become active now. It did its job, now the results are getting summarized, and with that, any moment, this should all be done and we should have a report. Here we go. Here's our summary report, and if we take a look at it, we can see that of course, it's not a lot of text because again, we're just using those search results, which only come with a little bit of text, but still it's a nice summary. And we got all of these links here, which we could now use to dive in deeper, or of course, which we could try to automate by adding another agent that actually visits those websites. Again, I'll share more details on how you could try doing that in the next lecture if you're interested in that. But this is an example for a multi-agent system with specialized agents that are working together. So I showed you this program here that has multiple agents working together. And as mentioned back then, it's up to you whether you want to call all these things agents, because not all of them are autonomous. But many people would call them agents because they're performing a task, they're working together, and they're using AI. Anyways, what's interesting about this program here is that we are using multiple agents, because technically that's not necessary. We could have built one powerful agent only. We could have built this research planner agent such that it's way more powerful. We could have named it research agent, so that it's not just about planning, but about conducting the entire research. And we could have given it more tools. One tool for deriving search terms, one tool for performing web search, and so on. And then we could have just had a conversation with that agent, and we could have asked it to go ahead and perform the research and trust that it uses the right tools at the right time. And that's the potential problem. Trust. We could have done this, and chances are that for this relatively simple application here, it would have worked without problems. Depending on the AI model you're using under the hood, if you're using a very small one that's not as powerful, chances are higher that the agent messes things up at some point. But chances are that it would have worked if you would have used a fairly recent model, like we are doing here. So why did I not go for a single agent? Well, because of that trust problem. We can build super powerful agents that can do it all. But often, in my experience, it's better to build specialized agents and to have them work together. Because the advantage of the workflow we built here is that it's pretty deterministic. We have that autonomous agent in a place where we need it because we're having a discussion with the user. We don't know what the user wants, so we need an agent that has some flexibility. But then thereafter, once we know exactly what should be done and in which order, there really is no reason to hope that a super powerful agent does it right. Instead, in my experience, it's better to have a kind of powerful agent for exactly the tasks where you don't know what's going to happen when, but to have specialized agents that have no room for errors or for doing the wrong thing whenever you know exactly what you want to do. And I know exactly that I want to derive search results here. I know exactly that I want to create a report here. And I know exactly which prompts should be used for that. I want to be able to tweak those prompts as a developer. I don't want to trust the AI to make the right decisions. And that's something important to take away here. Just because you can give a large language model indirect access to tools, and just because you can build pretty autonomous, powerful agents, does not mean that you need to do that all the time. Very often, it's better to combine multiple specialized agents instead of building one super powerful, extremely flexible agent where you then have to hope that it does the right thing. Now, again, back at this project I showed you before, this research project here, there is something else that's interesting in here. Because in this project, we can actually see two types of memory being used. And memory management is an important concept when working with AI models and agents. And with that, I don't mean your computer memory. I don't mean your hardware resources. Instead, I'm talking about the memory of your agents, so how data is stored. And here we can typically differentiate between short-term and long-term memory. And the short-term memory is relevant for information that belongs to one session, to one agent maybe. Something like the chat history or results derived by one agent. That would be short-term because it's discarded once the program ends or once an agent is done. It's therefore often stored in computer memory, so in your RAM, or maybe in other short-term data stores. You could be using a memory-only database or something like this. You could be using something like Redis if you're building a more complex system. It's short-term though. So if you lose the data, that's no problem, and that's indeed intended. The idea is not to keep this information, this data around forever. Now, it can be shared across multiple agents, either by returning data and passing it as an input to the next agent, as I did it in my example, or by storing it in some global variable or anything like that. And then you also have long-term memory, and that's about storing information across multiple sessions or executions, so data that should not be lost when the program ends or an agent is done. Here we're talking about things like user preferences, or maybe results you want to use in the future. Since it should be stored long-term, this kind of data is typically stored in databases or files, either on your computer or on some server in the cloud, wherever. And of course, it may also be accessed by multiple agents, because it's just in a database. Any agent that needs access to it can reach out to it if you provide the right logic or the right tools, of course. And in this demo application here, we actually have both. This research planner agent, for example, manages a chat history. It stores all the user messages in the chat history, and it stores all its own replies in that history. And that's important because whenever you're sending a prompt to a model, to an AI model, no matter if it's a model by OpenAI, if it's an open model hosted on your machine, doesn't matter. Whenever you do that, this model only sees what you send it. So if you don't include an entire chat history, then this history is not available to it. Now, for some prompts, for many use cases, this might not matter. You might only need one prompt. But here, for example, where the entire history, the entire discussion, including results of tool calls and so on, where this all matters, it's crucial that you manage this short-term memory, that you manage this chat history so that you can send it to the AI model with future requests so that this history is available to the model. That's the idea here. It's then discarded when the agent is done because we're not doing anything with that chat history thereafter. We are, however, of course, returning our research plan, and you could treat that as short-term memory as well, because that research plan is then handed off to the next agent in line. So that is something to keep in mind. But that's all short-term memory. But this demo application here also has long-term memory because we have a database. And in that database, I'm storing research plans. For that, I created some tools that interact with that database, and I'm exposing these tools to one of my agents. Therefore, this agent, the research planner agent, which has access to these tools, has access to the long-term storage. And this is a long-term data store because these research plans, in this case here, should be available in the future too. If I start a new research session in the future, I want to be able to tap into those plans and reuse them. That's the idea. And therefore, when you're building your own agentic systems or AI-powered workflows, you also, of course, might want to consider which kind of data should be stored in the short term, or which kind of data you might want to persist a bit longer so that you can also use it in the future. You don't need to overthink it. Normally, these decisions will come naturally because you might need something like a chat history for the program to work the way it should work. But still, it's important to know about these two concepts also because you'll encounter these terms quite a bit when working with agents created by others. And that's it for this section. In this section, you learned how you can build truly autonomous agents by giving them tools. And you also learned how these tools work and that it's not the large language model that calls the tools, but that it's instead just describing some intent to call a tool. You also learned that the definition of an agent is kind of blurry because often people call anything that uses AI an agent. And we also did that here in this research project where 2 of the 3 agents are not autonomous. But that is fine because ultimately you don't need to have a hard differentiation between workflows and agents. Ultimately, it's all about building AI-powered applications that get a certain job done, that automate a certain problem, for example. And for that, you can use all these tools and all these things you learned in the previous section and in this section here to build these workflows and these tools and automations in exactly the way you need. In this section, and also in the section before, we build workflows and agents from the ground up. I mean, I gave you the code, but it's all built from the ground up. No special third-party package that does the work for us. Instead, it's all raw Python code. Because the idea behind this course is to give you the knowledge you need so that you feel confident building your own agents, so that you can use what you learn in this course to start writing your own code. Because as you hopefully see, whilst things can get a bit more complex and you can build more complex workflows, ultimately, it's really not that hard to wire up a large language model with some tools and prompts and automate some tasks. But you don't have to build it all on your own if you don't want to. If you are working on more complex projects, if you don't need full control, which is the advantage you have if you build things from the ground up on your own. But if you don't need that and if you don't want to build everything from your own, You don't have to, because there are plenty of third-party libraries and SDKs out there that more or less simplify the task of building AI agents and AI workflows. And this is just a small selection. LangGraph and LangChain, Crew AI are amongst the more popular solutions about which you maybe already heard. OpenAI and Google and other providers as well have their own SDKs, which make it particularly easy to work with their models and build agents and workflows with their models. And as mentioned, there are plenty of others. Just for fun, I also asked ChatGPT about that, and it gave me a long list of libraries and SDKs I could consider using if I wanted some help with building AI agents and workflows. And therefore, now with the knowledge you have about how AI agents work, what they are, how you can combine them, how tools are getting used behind the scenes, and what the idea behind AI workflows is, with all that, you can definitely reach out for tools and helpers like these to make your life a bit easier if you need to build more complex AI systems and agents. In the next lecture, we'll have a first brief look at one of these tools to get you started with it. So there are plenty of SDKs and libraries you can use to more or less simplify the process of building AI workflows and agents. Now, in my experience, right now, when I'm recording this, amongst the most popular solutions are LangGraph and LangChain. These two kind of belong together. They are by the same team and they work together. And Crew AI. Now, LangGraph is definitely one of the most popular tools out there. It's getting used quite a bit, but in my experience, it can feel a bit over-engineered, especially when you're getting started with it. You can definitely explore it. It is popular, as mentioned, but since LangGraph is a tool that tries to give you a lot of features and a lot of configuration options, building something simple like a chatbot can initially maybe feel a bit overwhelming, especially once you start giving that thing tools. For me, it kind of felt easier to build it from the ground up myself, as I did it in this section and in this course, than to use LangGraph. But of course, it's just a learning curve, and the more you use it, the more you get used to it, and the more powerful things you can build. But for getting started with such agent SDKs, libraries that help you build agents and workflows, I would recommend Crew AI instead. And of course, you can also explore both or whatever you like. But Crew AI, in my experience, is a bit easier to wrap your head around initially. It's a bit easier to get started with. And that's therefore the library I want to get you started with here in this lecture. And for that, as a first step, you must make sure, if you want to follow along, that you have the Crew AI tool installed on your system. Attached, you find a link to their installation guide, which contains these installation instructions. And actually, they start by installing UV, which you might recall is the Python package and project management tool I also used in this course. So maybe you already have it installed if you did follow along with that. Once you got UV installed, you can use this UV tool to install the actual Crew AI tool by running this command in your terminal or command prompt, no matter which operating system you're using. And once you got that installed, you are ready to create a Crew AI project. And you can do that by opening up your terminal or command prompt and navigating into a place on your machine where you want to create that project. And then there, you can run Crew AI, which is a command that should now be available now that you installed the Crew AI tool. Create Crew, and then research Crew. Now, this is a predefined starting project by the Crew AI team that makes it a bit easier to get started with Crew AI. If you hit enter, this starts creating a new folder in the place where you ran the command, a folder named Research Crew, and it asks you which model provider you want to use. Now, as you see, you got a long list of providers to choose from. I will go with OpenAI here because I've been using that throughout the course, and in my experience, Crew AI sometimes struggles with some of these providers. For example, with Olama, I had some problems when trying to use these locally running models. I think related to a third-party package used under the hood by Crew AI, but nonetheless. And therefore, I'll use OpenAI here. So that's my choice. And for the model, I'll go with GPT-4o and therefore choose option 5 here. Of course, you can choose any model you want, and by the time you're viewing this, these models will most likely already have changed. Then you can enter your Open API key here, and no worries, you're not sharing that with the Crew AI team or anything like that. Instead, it'll just put that into a .env file for you. So I did that here, and with that, that project was created, and I did now open it up in Visual Studio Code again. Now, if anything about that doesn't work, or if you're getting a different folder structure or anything like that, attached you find the project as it was created for me, so you can use that. In that project, as a first step, you should run uvsync or Crew AI install to install all the dependencies, all the third-party packages that are being used by this project. So that's something I did here. And with that, we're ready to dive into this project. Now, what's really great about this project here, and that's one of the reasons why I chose it, is that it is a project that was created by the Crew AI team, so it uses all their recommendations, best practices, and so on. But it's actually tackling a similar problem as my research demo I showed you earlier in the section, where all the code was written by me. Now we're doing almost the same thing, but with a third-party library that hopefully makes our life easier. So let's see what we got here. The idea behind Crew AI, behind this package, is that you create so-called crews. And a crew is simply just a collection of agents, a team of agents, you could say. Therefore, every crew is made up of a bunch of agents. And agents are registered by simply adding methods to such a crew class, which is decorated with the crew base decorator. And decorators are simply a Python feature that do stuff to the thing they're attached to behind the scenes, so that transform the thing to which they are attached to behind the scenes. So we have a research crew class, and in that we have a researcher method, and that method is decorated with that agent decorator, and behind the scenes, the Crew AI SDK, which we're using in this package, and which will run our code in the end, that SDK, that tool, is registering this method as an agent in that crew. So that researcher here is the first agent we're adding. And therefore, it makes sense that this method actually returns an agent object by instantiating that agent class. Now, where is this agent class coming from? Well, that is coming from the Crew AI SDK. So just as I showed you a base agent class that I created in my code, here we're getting an agent class by this third-party package. Internally, it will very likely do more than my basic agent class in my code, but it's generally the same idea, you could say. So we're creating an agent here, and we're registering it by returning it in a method which is decorated with agent. And the same is done here with the reporting analyst, another agent in this crew. So the idea is that we have a crew with two agents, one that seems to be responsible for researching things, and the other that seems to be responsible for creating reports. Again, not that far away from the example I showed you. Now, we have more in there, but before we get to that, there's one important question. How exactly are these agents configured? How do they know what they should do and which tools they have? Good question. At the moment, they have no tools, but they have some configuration. And that is loaded here. And it's actually loaded with help of the Crew AI package. So this agents config thing here, which is coming from the base agent class, that is some functionality, some logic provided by the Crew AI package. And what this does is it actually loads the configuration from an external file, specifically a file that can be found in this config folder, which is also part of that created project. In this config folder, we have an agents.yaml file, which contains all the configurations for all the agents you want to have. And of course, you can edit this to add more configurations for more agents. And a tasks YAML file, which will describe the tasks, and I'll get back to that. So let's take a look at agents YAML. In there, we have two agent configuration objects, if you want to call it like this. And if you were to add a new agent, you could simply do so by adding it here, like an evaluation agent, maybe just called evaluation. And every agent then has a role, a goal, and a backstory, which in the end is used by this Crew AI SDK to construct a system prompt, a developer prompt that will be used behind the scenes. And in general, to adjust the prompts that reach the large language model. So what we did by hand in our code, what we had to write by hand in our code, is done automatically for us here in this project when using Crew AI. And this configuration is used as a base. Now what you'll see in this configuration is that there are some placeholders for the topic here, for example. And these placeholders will be filled with concrete values by the time the agent runs. Because the idea is that, of course, every configuration might need some dynamic, flexible elements. Like, for example, here for the researcher, we don't know the topic this agent will be used on in advance. When we write the code for this agent, we of course don't know which topic it will cover, because the idea is that we have a flexible agent that can cover all kinds of topics. So this is a placeholder that will be populated by the time we run the agent. And I'll show you how it's populated in just a second. But that's the configuration for our agents. And with that, we have configured agents that are being registered. Still, no tools. And therefore, depending on your definition, not really agents. But we talked about this before. Now, before we give at least some of these agents some tools, let's see what else is in this crew.py file. Because we also have tasks, not just agents. Tasks are what the name kind of implies. They're the tasks these agents should work on. So we have a research task, which will probably be fulfilled by the research agent, and a reporting task, which will be handled by the reporting agent. And the idea is that you could define multiple tasks and also define multiple tasks to a single agent. Here we have two tasks for two agents, so one task per agent though. Now, just like agents, tasks are configured with help of external configuration files. And that's what this tasks.yaml file is there for. In that file, we find two task definitions because we have two tasks, and every task has a description that describes what the task is about. And we also can have placeholders here, which makes sense because we might want to perform the same kind of task on different inputs, on different topics. We have an expected output that should be produced by the agent for this task, and we also assign which agent will perform this task, which of course is important to know. So you can think of these descriptions here basically as the user prompts that are sent to the large language model. The agent definitions here could be the system prompts, which in general control how the agent should behave. And then for the different tasks, we have the specific task descriptions that are sent as user prompts to the large language model, kind of. So that's the task definitions file. Back in the crew.py file, we can also see that the second task has an output file configuration, which means that its output will not be funneled into another agent, but instead into a file. Because we know that here for this program, for this crew, will be done once the reporting task is completed. And the results should be stored in a report.md file. And of course, I know all that from the official docs. That's of course the place to dive into if you want to learn more about Crew AI. Speaking of funneling results from one agent to another, that is what's happening behind the scenes here. So what we did manually in our code is done for us here by the Crew AI package. And it is done for us because of this last thing here in the research crew class in the crew.py file. Here the overall crew is defined and registered. And that happens by returning a crew object based on the crew class. It's here where all these agents are then assigned to this crew and where the tasks are assigned. This process thing here controls that they are executed in order. And with that, the overall crew is registered and ready to go. That's the idea here. And behind the scenes, because all these agents and tasks belong to the same crew, the output from one task, which was handled by one agent, is provided to the next task in the next agent. That happens behind the scenes automatically on our behalf. And that's all. But this is not too useful because none of these agents has any tools, so they won't really be able to do any valuable research. To make these crew AI agents a bit more useful, I want to give them access to tools. At least I want to give one agent access to a tool. And we can do that by adding a new package, for example with uv-add. And the package I want to install is crew AI square brackets tools, written like this. This is an extra package which you will probably install in many crew AI projects because this package unlocks many pre-built tools that you can use in your AI agents, in your crew AI agents. Because what's really great about crew AI is not just that it gives you these building blocks for agents, tasks, crews, and a couple of other things, but that they actually also give you quite a lot of tools that already exist that you don't need to build on your own. Like, for example, search and research tools. And here you see you got various tools for integrating third-party services into your crew AI managed application. Like, for example, Brave Search, which I used in my project as well. What a coincidence. So here we see that we need to install this crew AI tools package, which we just did. And then using this Brave Search is super simple. We just need to add an environment variable called Brave API key to our environment. And you can easily do that by editing this .env file, which was created for you by this crew AI tool. So in there, I added my Brave API key, written like this. That's important. It will be loaded for you automatically. And then that's almost all, because now you can go back to your crew and to the agent that should be able to use this tool, and you can add an extra configuration option to this agent constructor function, an extra parameter you pass to it, and that's the tools parameter. And this tools parameter simply takes a list of all tools you want to expose to this agent. Now, of course, you can also create custom tools if you want to. Just to make sure that this is clear, you can absolutely do that. But here, to use that Brave Search tool, all we have to do is use the Brave Search tool like this and make sure it's getting imported. So from Crew AI tools, we want to import the Brave Search tool, which we can do because, again, it comes pre-built with Crew AI, so to say. They are providing it to you. So with that added, we just have to instantiate it like this, and that's all. The search term for this tool will be produced by the researcher, by this agent. The description for how to use this tool will be generated behind the scenes by the SDK. So just to be clear, it'll still work as explained before in this course. The large language model will not directly use the tool, instead it will just get a description of the available tools and how these tools can be called, how they can be requested to be precise. But this description of the tool, of the function in the end, that's created behind the scenes by Crew AI, by this SDK for you. That's what's happening. And that all happens just because we registered it like this, which is of course pretty convenient. And with that, this agent can call this tool here whenever it needs to. And therefore now we got a finished basic research crew with 2 agents that can perform web search and create a report. Now, the solution I gave you, the workflow, the program I gave you, was able to do more than that. We had an agent for creating a research plan in conjunction with the user, and we had an agent that then derived multiple search terms and performed the web search, and then we had the summary agent. We had more than what we have here, but still, it's interesting to see how you can solve a kind of similar, a bit simpler problem with a third-party package instead. So therefore, now with everything out of the way, we can open up the terminal, navigate it into this project, and simply run crew AI run. And that will then run this crew. However, before we do that, one important note, it's here in main.py where you control how this crew will be executed. And it's here where the actual input values for these dynamic inputs will be set. You remember we had these dynamic inputs like topic, or for the task here, the current year. The concrete values are set here in main.py, and at the moment they're hard-coded. So if you want to be able to do research on your own topics, if you want to be able to set those topics on your own, you can either edit this code, or you can of course just add an input function and ask the user, so you, for the topic whenever this program runs. You just need to make sure that you then pass this topic as a value for this topic key here in this dictionary. Because this inputs dictionary is then fed into the crew when it's kicked off. And if you had more dynamic fields, you would also add them here, of course. And with that, we can now run crew AI run, and then we should get asked for a research topic once this is up and running. So it can take a while. I'm getting some warnings here. You can ignore them though. And then here I'm getting asked for the research topic. So I'll say recent developments in generative AI. And now Crew AI is kicking off this research process by running these tasks through the defined agents. It's performing this web search, getting these results, analyzing the results with the agents, and then in the end, we should get a report. And under the hood, it's doing kind of the same things we did manually in our code. But now here, of course, we have to write a bit less code, which can be an advantage. But you therefore, of course, also have a bit less control. It's always a trade-off. So here we go. The report is done. It's also saved in this report.md file. And as you can see, these are the results this crew produced for the given instructions in these configuration files and the topic I decided. And therefore using tools, SDKs like Crew AI or LangGraph or one of the many other SDKs you find out there that aim to help you with building AI agents can definitely be worth a closer look. I would recommend that you simply play around with them to find out if they get the job done for your specific tasks. You should never forget though that you can also build things on your own, and that for some workflows, building things on your own might actually be more straightforward and gives you more control. But ultimately, you should experiment and find the best tool for your specific problem.